There's a clock on the International Space Station. Right now, this very moment, this clock is running slower than the clock on your wrist. Not by much, we're talking microseconds per day, but measurably, detectably slower. The astronauts orbiting Earth are, in a very real sense, aging more slowly than people on the ground below them. This isn't some theoretical possibility or a thought experiment. This is happening right now. This is real. And if you know about it, if you understand what's happening, it's one of the most profound and beautiful truths about the nature of reality. Time is the one thing that we take for granted. Time flows. Seconds tick by. The past is behind us. The future ahead. Time is absolute, unchanging, the same everywhere. That's what our intuition tells us. That's what our everyday experience suggests. But our intuition is wrong. Our everyday experience is misleading. Time isn't absolute. Time is relative. Time runs at different speeds in different places. And the universe is designed in such a way that this difference matters profoundly for how everything works. This is one of the strangest and most counterintuitive discoveries in the history of physics. It upends our basic assumptions about reality. It suggests that the universe is far stranger, far more wonderful, far more interconnected than we ever imagined. And yet it's been confirmed by countless observations. It's real. It's happening. It's one of the most beautiful insights into how the universe actually works. The story starts with a simple observation that bothered physicists in the late 1800s. The speed of light is constant, about 299,792 kilometers per second to be precise. This is true in every experiment anyone has ever done. No matter how fast you're moving, no matter what direction you measure it, light always travels at the same speed. But this seems deeply weird. Consider how speeds work in everyday life. If you're driving a car at 100 kilometers per hour and a car ahead of you is also driving at 100 kilometers per hour, from your perspective, that car isn't moving. You're both going the same speed, so the relative speed is zero. But if you're moving at 100 kilometers per hour and light is moving at 299,792 kilometers per hour, light is moving faster than you. The relative speed should be about 299,692 kilometers per hour. That makes intuitive sense. That's how speed should add and subtract. But here's the problem. If you then measure the speed of light while moving in the opposite direction, while moving toward a light source instead of away from it, you get the same answer. 299,792 kilometers per hour. How is this possible? It's like this. Imagine you're standing by a highway. A car passes you at 100 kilometers per hour. You measure its speed as 100 kilometers per hour. That makes sense. Now imagine you're moving toward the highway at 50 kilometers per hour and the same car passes you. You measure its speed, accounting for your own motion. You'd expect to measure 150 kilometers per hour, 100 plus 50. But what if, no matter what, you always measured the car's speed as 100 kilometers per hour? What if, whether you were standing still or moving toward or away from the car, the measured speed was always the same? That would be bizarre. That would violate everything we know about how speeds work. Yet this is exactly what happens with the light. And this puzzle bothered physicists for decades. In 1887, two American physicists named Albert Michelson and Edward Morley conducted an experiment specifically designed to measure the speed of light while the Earth moved through space. They expected to get different measurements depending on the direction they measured in. Earth orbits the Sun, so Earth is moving through space. Depending on whether they measured light moving in the same direction as Earth's motion, or perpendicular to it, or opposite to it, they expected different results. They built an incredibly sensitive instrument called an interferometer. It split light into two beams that traveled perpendicular to each other, reflected off mirrors, and recombined. If the speed of light was different in different directions, the two beams would recombine out of phase, creating an interference pattern. By measuring this pattern, they could detect the difference. But there was no difference. No matter which direction they measured, the speed of light was the same. This result was shocking. It contradicted some expected outcome, and it sparked decades of confusion and theorizing. Some physicists proposed that space was filled with a medium called the ether, through which light propagated. Maybe the Earth was moving through the ether, and this affected the speed of light measurements somehow. But no evidence for the ether could be found. Others proposed other explanations, but none of them really worked. The puzzle remained. How could the speed of light be constant in all reference frames? This seemed to violate basic physics. Einstein's answer, published in 1905 when he was working at the Swiss Patent Office in Bern, was radical in a way that's hard to overstate. He didn't try to explain how the speed of light could be constant through some complicated mechanism. Instead, he said, maybe the speed of light being constant is just a fundamental fact. No, and if that's true, then something else has to give. Something else has to be variable. And that something else is time. Einstein's theory of special relativity, published that year, proposed something that would have seemed absurd to any physicist before it. Time is not absolute. The flow of time depends on your motion. To understand this, you have to think about what we mean by time. How do we measure time? We measure it by counting oscillations, the swings of a pendulum, the vibrations of a crystal, the ticks of a clock. Time is fundamentally measured by counting some repeating process. But here's the key. The rate at which a process repeats depends on how fast the process is moving through space. This is because of the constancy of the speed of light and the way light propagates through spacetime. If you're moving fast relative to an observer, the repeating processes that measure time, your heartbeat, the vibrations in an atomic clock, the decay of radioactive particles, all appear to happen more slowly to the stationary observer. From the stationary observer's perspective, time is literally running slower for you. This is not an illusion. This is not just about how things appear. This is actual real-time dilation. Your clock genuinely runs slower. Your biological processes genuinely slow down. If you're moving very fast relative to Earth and you return to Earth, you will have aged less than people who stayed on Earth. You will be younger than your friends. This phenomenon is called time dilation, and it's described mathematically by a simple formula. The factor by which time dilates is gamma equals 1 over the square root of 1 minus v squared over c squared, where v is your velocity and c is the speed of light. At everyday speeds, driving a car, flying a plane, even orbiting Earth in the International Space Station, this factor is incredibly close to 1. So the effect is tiny. For example, astronauts on the International Space Station, orbiting at about 28,000 kilometers per hour, experience time dilation by a factor of about 1.0000000003. That means time passes about 0.00003% slower for them Over the course of a year in space, they age about zero point 0.4 seconds less than people on Earth. This is small enough that it's hard to measure directly, but it's real, and it's been measured by atomic clocks on the space station and compared to clocks on Earth. But as you move faster, approaching the speed of light, the effect becomes dramatic. At half the speed of light, gamma is about 1.15. Time passes about 15% slower for you. At 90% the speed of light, gamma is about 2.3. Time passes about 2 1/3 times slower for you. At 99% the speed of light, gamma is about 7. Time passes 7 times slower for you. At 99.9% the speed of light, gamma is about 22. Time passes 22 times slower for you. As you approach the speed of light, gamma approaches infinity. Time approaches stopping completely. This means that if you could build a spaceship that traveled at 99.9% the speed of light, and you took a trip to a star 1,000 light years away, from Earth's perspective, the trip would take about 1,000 years. But from your perspective, inside the spaceship, the trip would take only about 45 years. You would experience only 45 years passing, while 1,000 years pass on Earth. When you returned, Earth would have aged 2,000 years, but you would have aged only 90 years. This is the famous twin paradox. Imagine you have a twin sister. At age 20, you leave Earth in a spaceship traveling at 99.9% the speed of light. You take a round trip to a nearby star 100 light years away and back. From Earth's perspective, you're gone for about 200 years. Your twin sister ages 200 years and lives a long life. But from your perspective, you're only gone for about 9 years. You age only 9 years. You return to Earth at age 29, while your twin sister is now 220 years old, if she were still alive. You're vastly younger than her. This seems impossible. How can both perspectives be true? The answer is that they both are true, because time isn't absolute. Time is relative. In your reference frame, 9 years pass. In your sister's reference frame, 200 years pass. Both measurements are correct in their respective reference frames. This was so counterintuitive, so weird, that many physicists initially rejected it. How could time not be absolute? How could two observers measure different amounts of time? But over time, as evidence accumulated, as the theory made successful predictions, the idea of time dilation became accepted. But Einstein didn't stop with special relativity. He spent the next decade working on a more complete theory. In 1915, he published his theory of general relativity, which extended the concept of time dilation to include gravity. Special relativity dealt with observers moving relative to each other at constant speeds. But what about acceleration? What about gravity? Gravity is one of the most fundamental forces in the universe. Any complete theory of space-time and time would have to account for gravity. Einstein's insight was profound. Gravity isn't a force pulling on objects the way Newton had described it. Instead, gravity is the curvature of space-time itself. Think of space-time as a fabric. Massive objects warp this fabric. The sun warps space-time around it. Earth warps space-time around it. You warp space-time around you, though the effect is incredibly tiny. In this curved space-time, objects don't feel a force pulling them. Instead, they're simply following the curved geometry of space-time. They're taking the shortest path through space-time, which is called a geodesic. And here's the key for time dilation. Time passes slower in regions where space-time is more curved. That is, time passes slower in stronger gravitational fields. This has immediate implications. Time runs slower near massive objects. Time runs faster far away from massive objects. On Earth, this effect is small. Time runs about 1 part in a billion slower at Earth's surface than it does far above in space. But the effect is real and measurable. This is why GPS satellites have to account for time dilation. A GPS satellite orbits Earth at high altitude, about 20,000 kilometers up. At that altitude, gravity is weaker than it is on Earth's surface. So time runs faster for the satellite than for clocks on Earth. Additionally, the satellite is moving at about 14,000 kilometers per hour, which causes special relativistic time dilation. Time runs slower for moving objects. This partially cancels out the gravitational effect. The combined effect is that time runs faster for GPS satellites by about 45 microseconds per day compared to clocks on Earth's surface. This sounds tiny, but if we didn't account for it, the GPS system would give wrong positions. GPS calculates position by measuring the time it takes for signals from multiple satellites to reach a receiver. If the satellite clocks were running fast by 45 microseconds per day, the calculated position would be off by about 10 kilometers per day. Within a week, GPS would be essentially useless. But because we account for time dilation, both the special relativistic effect from the satellite's motion and the general relativistic effect from the weaker gravity at high altitude, GPS works perfectly. Every time you use GPS to navigate, you're benefiting from Einstein's theory of relativity. Near a black hole, the effect is extreme. Black holes are objects so dense that their gravity warps space-time to an extreme degree. At the event horizon of a black hole, the point of no return, space-time is curved so severely that time essentially stops. If you were somehow suspended just outside the event horizon of a black hole, watching someone fall in, their clock would appear to slow down. The person falling in would appear to take forever to cross the event horizon. From your perspective, they would appear frozen at the event horizon. But from the falling person's perspective, they would cross the event horizon in finite time. From their perspective, they wouldn't notice anything special about time at the event horizon. Time would be passing normally for them. They would cross it and a short time later be destroyed by the tidal forces inside the black hole. This is one of the strangest aspects of black holes. Different observers disagree about what's happening near the event horizon. From one perspective, time stops. From another perspective, time passes normally. Both are correct in their reference frames. So time dilation is real. It happens because of motion, special relativity, and because of gravity, general relativity. And it's been confirmed by countless observations. Let me talk about some of the most compelling evidence. One famous observation involves muons, particles that are created when cosmic rays hit Earth's atmosphere. Muons are unstable. They decay very quickly. If you create a muon at rest and let it sit, it will decay in about 2 millionths of a second, specifically 2.2 microseconds. This is the muon's lifetime in its own rest frame. Now, when cosmic rays hit Earth's upper atmosphere, they create muons. These muons are moving downward at very high speeds, typically about 99.5% the speed of light. They're moving so fast that they have very little time from their rest frame perspective before they decay. If muons decayed at their normal rate, only about 1% of the muons created in the upper atmosphere would survive to reach Earth's surface. The rest would decay before getting there. But in reality, about 21% of them reach Earth's surface. We detect them all the time. How is this possible? The answer is time dilation. The muons are moving at 99.5% the speed of light. From Earth's perspective, time is running slower for them. Their decay is happening in slow motion, in a sense. So they have more time to travel through the atmosphere before decaying. We can calculate exactly how much time dilation affects the muons. At 99.5% the speed of light, gamma is about 10. Time runs about 10 times slower for the muons than for stationary observers on Earth. So from Earth's perspective, a muon's lifetime is extended from 2.2 microseconds to about 22 microseconds. With a 22 microsecond lifetime traveling at 99.5% the speed of light, a muon can travel a distance of about 6.6 kilometers before decaying. This is roughly the altitude at which muons are created in the atmosphere. If we predict what fraction of muons will reach Earth's surface, accounting for time dilation, we get about 21%, and that matches what's actually observed. This is direct evidence of time dilation. The muon observation is so famous in physics classes that it's often called the muon test of special relativity. It's one of the simplest and most direct demonstrations that time dilation is real. Another observation involves GPS satellites, which I mentioned earlier. GPS satellites orbit Earth at an altitude of about 20,200 kilometers. At that altitude, they move at about 3.9 kilometers per second, about 14,000 kilometers per hour. There are two effects on the satellite clocks. First, because the satellites are moving, special relativistic time dilation makes their clocks run slow by about 7 microseconds per day. Second, because the satellites are at high altitude where gravity is weaker, general relativistic time dilation makes their clocks run fast by about 45 microseconds per day, compared to a clock at sea level. The net effect is that satellite clocks run fast by about 38 microseconds per day compared to clocks at sea level. The signals from GPS satellites encode the time at which they were sent. A receiver on the ground calculates its position by measuring the time it takes for signals from multiple satellites to arrive. The receiver compares the time encoded in the signal with the time according to its own clock. If the satellite clocks are running fast compared to clocks on the ground by 38 microseconds per day, and we didn't account for this, the receiver would calculate incorrect positions. Light travels at 300,000 kilometers per second. In 1 microsecond, it travels 300 meters. So an error of 38 microseconds per day corresponds to an error of about 11 kilometers per day in GPS position calculations. GPS satellites actually correct for this by running their clocks slower than normal, by programming in a correction factor so that their clocks run at the same rate as clocks on Earth's surface, roughly. This correction is based on Einstein's predictions about time dilation, and it works perfectly. Without accounting for time dilation, GPS would accumulate errors of about 11 kilometers per day. It would be essentially useless for navigation. Every time someone uses GPS in a car, on their phone, in an airplane, they're using a system that works only because we account for Einstein's predictions about time dilation. Another observation involves neutron stars. Neutron stars are incredibly dense objects, the remnants of massive stars that have collapsed after going supernova. A neutron star might have a mass of 1.4 times the mass of our Sun, compressed into a sphere only about 20 kilometers in radius. The gravity at the surface of a neutron star is enormous, about 200 billion times stronger than Earth's gravity. Time dilation effects near neutron stars are significant but not extreme. They're much less extreme than near black holes. We can observe radiation from material falling into neutron stars or orbiting them. By analyzing the properties of this radiation, its frequency, its intensity, how it changes over time, we can determine properties of the neutron star and test whether general relativity's predictions about time dilation are correct. The observations match Einstein's predictions. Time dilation near neutron stars is exactly what general relativity predicts. Yet another observation involves atomic clocks. Atomic clocks are incredibly precise. They can measure time accurate to within 1 second in millions of years. In 1976, two physicists named Hafele and Keating flew atomic clocks on airplanes around the world. They compared the clock readings to clocks that stayed on the ground. The flying clocks showed less elapsed time than the ground clocks. They had aged less. This was direct evidence of special relativistic time dilation due to the clock's motion. The difference was tiny, about 200 nanoseconds, billionths of a second. But it was measured precisely and exactly matched Einstein's predictions. More recent experiments have done even more precise tests. In 1971, cesium beam atomic clocks were flown around the world on commercial aircraft, and the time dilation was measured. The results agreed with Einstein's theory to within the precision of measurement. In 1979, hydrogen maser clocks, which are even more precise than cesium clocks, were flown in an airplane, and the time dilation was measured even more precisely. Again, the results matched Einstein's predictions exactly. So we have abundant evidence that time dilation is real. It's confirmed by observations of muons, by the success of GPS, by observations of neutron stars and black holes, and by direct measurements with atomic clocks. But what does this mean? What are the implications of time dilation? How should we think about reality if time isn't absolute? The implications are profound and far-reaching. They touch on the fundamental nature of reality, causality, the future, and even the nature of consciousness. First, there's no absolute now in the universe. In our everyday experience, there's a present moment, now. Events that happen now are simultaneous, but in relativity, this breaks down. Events that are simultaneous in one reference frame are not simultaneous in another reference frame that's moving relative to the first. This is because simultaneity is related to time, and time is relative. If two observers are moving relative to each other, they disagree about which events are simultaneous. For observer A, two events happen at the same time. For observer B, one event happens before the other. This is called the relativity of simultaneity, and it has profound implications. It means that the universe doesn't have a single present moment that's the same everywhere. Different observers moving at different speeds or located in different gravitational fields have different present moments. This is hard to accept intuitively. We feel like there's an objective now that's the same everywhere. But relativity says there isn't. A second implication is about the nature of the future. If there's no absolute now, then what does it mean for something to be in the future? In our everyday thinking, the future is not yet happened. But if there's no absolute now, then the division between past, present, and future becomes observer dependent. Some physicists argue that this means the entire spacetime, past, present, and future, all exist equally. The future isn't not yet, it's just not here. This perspective is called eternalism, and it's a radical departure from our everyday intuition. Other physicists argue that only the present exists, and the future doesn't exist yet. This is called presentism. But presentism is hard to reconcile with relativity, since there's no absolute present in relativity. Still others argue for growing block universe where the past and present exist, but the future doesn't exist yet. The now is the edge of the growing block. But this also has problems with relativity. These are deep philosophical questions, and physicists and philosophers still debate them. A third implication is about time travel and causality. Can you travel to the past? Can you change events that have already happened? General relativity doesn't forbid closed time-like curves, paths through space-time that loop back to earlier times. Mathematically, solutions to Einstein's field equations can include such curves. The most famous example is the Tipler cylinder, a rotating cylinder that, if long enough and spinning fast enough, could create a closed time-like curve. But actually creating a closed time-like curve seems to require exotic matter with negative energy density, which we've never observed. It also requires enormous engineering feats. So while general relativity doesn't forbid time travel, it's probably not practically achievable. But even if time travel were possible, there's the problem of causality and paradoxes. The most famous paradox is the grandfather paradox. If you travel to the past and kill your grandfather before your parent was born, you would prevent your own birth. But then you wouldn't be able to travel to the past to kill your grandfather. This is a logical contradiction. Most physicists think the universe prevents such paradoxes through some mechanism. One possibility is the Novikov self-consistency principle. You can travel to the past, but anything you do in the past is already part of history and can't be changed. The grandfather you try to kill would always escape your attempt. You could never actually kill him because you didn't kill him in the past. Another possibility is the many worlds interpretation. When you travel to the past and kill your grandfather, you create a branch in the timeline. In the original timeline, your grandfather lived and you were born. In the new timeline, your grandfather died and you were never born. Both timelines are consistent because they're separate. These are fascinating questions, but they're also quite speculative. We don't know if time travel is actually possible, and we don't know how the universe would handle the paradoxes if it were. What we do know is that time dilation is real and confirmed by observation. Time is relative. Time runs at different rates in different places. And this fundamental truth about reality has been woven into the fabric of how the universe works. There's another phenomenon directly related to time dilation that deserves detailed attention: gravitational redshift. This is one of the most direct and beautiful ways to observe time dilation in nature. Light is made up of photons, each with a frequency and wavelength. Red light has a lower frequency and longer wavelength than blue light. When light travels from a region of strong gravity to a region of weak gravity, it loses energy. This causes its frequency to decrease and its wavelength to increase. It gets shifted toward the red end of the spectrum. This is gravitational redshift. The reason this happens is directly related to time dilation. Light emitted in a strong gravitational field is observed to have a lower frequency by someone in a weak gravitational field. This occurs because time runs slower in strong gravity, so the frequency of oscillation is lower. Think of it this way. Light is like a clock, oscillating at a certain frequency. If time runs slower where the light is emitted, then to an observer where time runs faster, the light's oscillations appear to be happening more slowly. The frequency is lower. We can measure gravitational redshift in several ways. Light from the sun, which has a strong gravitational field, is gravitationally redshifted compared to light from empty space. The amount of redshift matches exactly what Einstein's general relativity predicts. In 1960, physicists Robert Pound and Glenn Riebke conducted a famous experiment using moose bower spectroscopy, an incredibly sensitive technique for measuring light frequencies. They sent light up a 22-meter tower at Harvard University and measured the tiny redshift as light climbed out of Earth's gravitational field. The fractional change in frequency is only about 1 part in a trillion, incredibly small, but they measured it. And it matched Einstein's prediction perfectly. This experiment, often called the Pound-Rebke experiment, is considered one of the most beautiful experiments in physics. It's simple in concept, send light up and measure the redshift, but profound in its implications. It's direct evidence that time passes at different rates at different altitudes. At the surface of a neutron star, gravitational redshift is enormous. A neutron star might have a mass about 1.4 times the mass of our Sun, compressed into a sphere only about 20 kilometers in radius. The gravity at the surface is billions of times stronger than on Earth. Light emitted at the surface of a neutron star is shifted by a factor of about 2 compared to light from far away. This means light loses about half its frequency as it escapes. Near the event horizon of a black hole, the effect is even more extreme. The time dilation factor near the event horizon becomes infinite. This means that light emitted at the event horizon, as observed by someone far away, has its frequency shifted to 0. The light takes infinite time to escape from the perspective of the distant observer. A person at the event horizon appears frozen, their clock appearing to stop from the distant observer's perspective. These gravitationally redshifted signals from the vicinity of black holes and neutron stars have been observed by space telescopes like Chandra and Suzaku. These observations directly confirm the time dilation predictions of general relativity. So gravitational redshift is one of the most direct ways to observe and measure time dilation. When you see starlight shifted toward the red because it's escaping a strong gravitational field, you're directly observing that time passes slower in strong gravity. You're seeing the universe reveal one of its most profound and beautiful truths. There's something almost spiritual about understanding time dilation. It means that time is not this absolute, unchanging backdrop against which events happen. Instead, time is woven into the fabric of reality, intertwined with space and gravity. Time is flexible. Time is relative. Time depends on where you are and how fast you're moving. It means that time is not this absolute, unchanging backdrop against which events happen. Instead, time is woven into the fabric of reality, intertwined with space and gravity. Time is flexible. Time is relative. Time depends on where you are and how fast you're moving. Before I continue with the philosophical implications, I want to dive deeper into one of the most extreme and beautiful applications of time dilation: black holes and what happens at their event horizons. A black hole is what remains when a massive star collapses. The star's matter is compressed to such an extreme density that it warps spacetime dramatically. At a certain radius from the center of the black hole, called the event horizon, the warping is so extreme that even light cannot escape. Anything that crosses the event horizon is forever cut off from the rest of the universe. The size of the event horizon depends on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would be about 3 kilometers in radius. For a black hole with the mass of Earth, the event horizon would be about 9 millimeters in radius. Now, what happens when you fall into a black hole? This is where time dilation becomes extreme and leads to some of the strangest physics imaginable. From the perspective of an observer far away from the black hole, watching you fall in, something strange happens. As you get closer to the event horizon, time dilation increases. From the distant observer's perspective, your clock appears to run slower and slower. Your movements appear to slow down. You appear to take longer and longer to reach the event horizon. In fact, from the distant observer's perspective, you would never actually reach the event horizon. You would appear to slow down asymptotically, taking infinite time to cross the event horizon. You would appear to be frozen there. Your clock stopped. Your image red-shifted to invisibility. But from your own perspective falling into the black hole, something different happens. You wouldn't notice time slowing down. From your perspective, time would pass normally. You would reach the event horizon in finite time, maybe in a second or a minute, depending on the black hole's size. However, once you cross the event horizon, something terrible happens. The tidal forces of the black hole would rip you apart. A black hole's gravity increases dramatically as you get closer. If you fell into a stellar black hole, the kind formed from a collapsed star, the tidal forces would be so extreme that you would be torn apart before reaching the event horizon. But if you fell into a supermassive black hole, the kind at the center of galaxies, millions or billions of times more massive, the tidal forces at the event horizon would be gentler, and you could theoretically cross the event horizon intact. But very shortly after crossing, you would hit the singularity, the infinitely dense center of the black hole, and be destroyed. This asymmetry between what the distant observer sees and what the falling observer experiences is one of the most profound consequences of time dilation. Two observers disagree completely about what's happening. The event horizon itself is a kind of boundary in spacetime. It's not a physical membrane, it's a surface defined by properties of spacetime itself. Nothing special happens at the event horizon from the perspective of someone falling through. But from the perspective of a distant observer, it's a barrier beyond which nothing can escape. Inside the event horizon, the structure of spacetime is such that all paths lead to the singularity. You can't avoid it. You can't travel parallel to the event horizon. All time-like paths that an observer could follow, lead to the center. This means that inside a black hole, the singularity is not in the future. It's in the future direction of spacetime itself. All paths lead to the singularity the way all paths lead to the future. This is profoundly strange. It suggests that inside a black hole, time and space are somehow exchanged. Near the singularity, spatial dimensions and the time dimension are related in a way that's hard to visualize. These are some of the deepest mysteries in physics. We don't fully understand what happens at the singularity. Our current physics breaks down there. We need a theory of quantum gravity to understand what's happening, but the time dilation effects around black holes have been observed. We've observed black holes by detecting the radiation from material spiraling into them. We've measured the effects predicted by general relativity, including time dilation. The observations match Einstein's theory. This changes how you think about the universe. When I think about time dilation, I think about the profound strangeness of reality. I think about how Einstein, through pure thought and mathematics, discovered something that nobody would have guessed about how the universe actually works. I think about how subsequent observations have confirmed this strange prediction. But time dilation doesn't just apply to everyday scales, or to astronauts in space, or to light from distant stars. It also applies at the scale of elementary particles. In particle physics experiments, time dilation is crucial to understanding how particles behave. Many elementary particles are unstable. They decay into other particles. Each particle has a characteristic lifetime in its rest frame, a timescale over which it's likely to decay. For example, a charged pion is a particle created in high-energy collisions. In its rest frame, it has a lifetime of about 26 nanoseconds. This means that if you could hold a pion still and measure how long before it decays, you'd measure about 26 nanoseconds. But in particle accelerators, we create pions moving at speeds close to the speed of light. Due to time dilation, their lifetimes are extended. A pion moving at 99.9% the speed of light would have a lifetime extended by a factor of about 22 times in the lab frame, so it would last about 570 nanoseconds before decaying. This is crucial for particle physics. We create particles in accelerators and they travel through detectors. If their lifetimes weren't extended by time dilation, they would decay before reaching the detectors, and we wouldn't be able to measure their properties. But because time runs slower for fast-moving particles, they last long enough to reach the detectors. We can study their properties and understand the particles and forces. Time dilation in particle physics is now routine. Every particle physics experiment accounts for it. Every particle physicist understands that fast-moving particles have extended lifetimes due to time dilation. The Large Hadron Collider, the most powerful particle accelerator in the world, located near Geneva, Switzerland, creates particles and accelerates them to 99.9999% the speed of light. The time dilation effects are enormous. Particles that would normally decay almost instantaneously in their rest frame last for measurable times in the lab frame. Without understanding time dilation, particle physics wouldn't work. We wouldn't understand the data from our experiments. We wouldn't be able to discover new particles or test our theories. So time dilation isn't just a theoretical curiosity or something that happens only in extreme circumstances. It's something that particle physicists use every day in their work. Time slows down in space. Time slows down near massive objects. Time slows down for fast-moving particles. These aren't metaphors. These aren't poetic ways of describing something else. This is literally what happens. Time actually moves at different rates in different places, for different observers, in different frames of reference. Now, I want to dive deeper into the physics that underlies time dilation. What I've described comes from Einstein's theories of special and general relativity, but understanding the fundamental principles behind them gives a deeper appreciation. The key to understanding general relativity starts with something called the equivalence principle. Einstein proposed this principle in the early 1900s, and it became the foundation for his theory of gravity. The equivalence principle states that being in a uniform gravitational field is equivalent to being in a uniformly accelerating reference frame. Think of it this way. Imagine you're in a spaceship far from any massive objects with no gravitational field. The spaceship's engines fire, accelerating at 10 meters per second squared, the same acceleration as gravity on Earth. From inside, you would experience the same effects as being on Earth. You would feel pressed against the floor. A ball dropped would fall at the same rate. Everything would feel exactly like Earth. Conversely, imagine you're freely falling in Earth's gravitational field, in an elevator with a broken cable. During the fall, you experience weightlessness. There's no apparent gravitational field. The equivalence principle says these situations are equivalent. The acceleration is what matters. This led Einstein to a profound insight. Gravity isn't a force. Gravity is the geometry of spacetime itself. Massive objects warp spacetime, they curve it. Objects moving through curved spacetime follow paths determined by the geometry. And because spacetime is curved differently in different places, Time passes at different rates. Time is part of spacetime. If spacetime is curved, time is affected. The mathematics of general relativity describes this curvature using the metric tensor. The metric tells you how to measure distances and time intervals in spacetime. Near a massive object, the metric is different from flat spacetime. The curvature is encoded in the metric. The metric tells you that time intervals are smaller near massive objects, time runs slower, and spatial intervals are distorted. For a spherical object like Earth or the Sun, the metric is described by the Schwarzschild metric, derived by Carl Schwarzschild just days after Einstein published general relativity. The metric involves a term that describes how time dilation varies with distance. Close to the object, time dilation is stronger. Far away, it approaches zero. For a black hole, the Schwarzschild metric predicts a singularity at the event horizon. At the event horizon, the time dilation factor becomes infinite. Mathematically, this expresses the fact that time appears to stop at the event horizon from the perspective of a distant observer. For rotating black holes, the metric is more complex. The Kerr metric. Rotating black holes have even stranger properties. They have an ergosphere where objects must orbit with a rotation. They exhibit frame dragging, where the black hole's rotation drags spacetime itself. All of these phenomena are consequences of curved spacetime described by Einstein's equations. This is the fundamental insight. Gravity is geometry. Time is part of geometry. Therefore, time is affected by gravity. Time dilation is a direct consequence of spacetime curvature, not a separate phenomenon. I find myself constantly amazed by this. The idea that time is flexible, that it's woven into the fabric of space itself, that massive objects curve spacetime and thereby affect how quickly time flows. This is one of the deepest insights in all of physics, and it's confirmed by observation. It's not just a mathematical curiosity, it's how the universe actually works. There's one more phenomenon I want to discuss that beautifully illustrates the deep connections between time dilation, gravity, and quantum mechanics. Hawking radiation. In the 1970s, physicist Stephen Hawking made a shocking discovery. Using quantum mechanics combined with general relativity, he showed that black holes aren't completely black. They emit radiation. How can this be? If nothing can escape a black hole's event horizon, how can radiation escape? The answer involves time dilation and quantum mechanics working together in a profound way. At the quantum level, spacetime is seething with activity. Virtual particle-antiparticle pairs constantly appear and disappear, borrowing energy from the vacuum for infinitesimal times allowed by the uncertainty principle. Near the event horizon of a black hole, something extraordinary can happen. A virtual particle-antiparticle pair appears near the event horizon. Due to the extreme gravity and time dilation at that location, one of the particles can fall into the black hole while the other escapes. The escaped particle appears as real radiation to a distant observer. This process removes energy from the black hole. The black hole has lost mass. Over cosmic timescales, a black hole can gradually evaporate by emitting Hawking radiation. The rate of emission depends on the black hole's mass. Large this altitude and their motion, time runs about 38 microseconds per day, faster for satellite clocks than for sea level clocks. This comes from two opposing effects: special relativistic time dilation from the satellite's high speed, 7 microseconds per day slower, and general relativistic time dilation from weaker gravity, 45 microseconds per day faster. Without accounting for time dilation, GPS would accumulate position errors of 11 kilometers per day. Within a week, GPS would be useless. But by programming Einstein's relativistic corrections into satellite clocks, GPS provides positioning accurate to meters. Consider what depends on GPS. Commercial aviation relies on it for navigation and fuel efficiency. Maritime navigation uses it to avoid hazards. Electrical power grids use GPS synchronized clocks to coordinate power distribution. Financial systems use GPS clocks for high-frequency trading. Cellular networks depend on GPS timing. Emergency services rely on GPS for location information. Billions of dollars in commerce and critical infrastructure depend on GPS, which works only because physicists understood time dilation. Every GPS navigation uses Einstein's theory. Every time you navigate using GPS, you're relying on a system that works because of time dilation. This is remarkable. Something so abstract and counterintuitive has such concrete, practical implications. Beyond GPS, time dilation affects other technologies. Particle accelerators like the Large Hadron Collider account for time dilation in their design and data analysis. Atomic clocks for precise timekeeping incorporate relativistic corrections. Satellites of all types benefit from accounting for relativistic effects, but the deepest implication is philosophical. We live in a universe where time is flexible, where time depends on your location and motion, where time isn't an absolute backdrop but a participant in reality's fabric. This challenges our intuitions deeply. We feel time flows uniformly everywhere, but that feeling is misleading. It comes from living in low gravity, low speed conditions where time dilation is negligible. If we lived on a neutron star surface, where gravity is billions of times stronger, time would flow 4 times slower for us compared to space observers. Traveling at near-light speeds in a spaceship, we would age much more slowly than Earth people. We would experience time's relativity directly. Understanding time dilation requires accepting that reality differs from intuition. It requires trusting mathematics and observation over subjective experience. This is a great lesson from physics. Reality is often strange. Reality doesn't always match intuition, but through careful observation and mathematics, we uncover profound truths about how the universe works. And those truths are more beautiful and profound than intuition could ever suggest. Now let me touch on something even more mysterious: the relationship between quantum mechanics and time. Time dilation operates at scales we can directly observe: moving objects, massive structures, planets, and stars. But what happens at the quantum level, where particles behave probabilistically? Quantum mechanics presents a puzzle about time we're still solving. In the Schrödinger equation, which describes quantum system evolution, time is just a parameter, like a coordinate. It's similar to space. But time seems different. We remember the past, not the future. Entropy increases forward in time. This directional aspect is called the arrow of time. Yet relativity suggests time and space are fundamentally similar, both part of spacetime. So where does time's arrow come from? One answer involves quantum measurement. In quantum mechanics, measuring a system causes its wave function to collapse. Before measurement, a particle might exist in superposition, multiple states simultaneously. After measurement, it's in one definite state. This measurement is irreversible. You can't unmeasure something. This irreversibility might connect to the arrow of time. The forward direction might be where measurements occur and information is revealed. But there's a puzzle. If the fundamental laws are time reversal invariant, meaning they look the same running forward or backward, how does measurement's asymmetry arise? This remains an open question. We don't fully understand how quantum mechanics relates to time's arrow. There's another mystery. What is time fundamentally? In relativity, time is a space-time dimension. In quantum mechanics, time is just an evolution parameter. Are these the same thing? Is time fundamental or emergent from something deeper? Some physicists speculate space-time might be emergent, that something more fundamental underlies it, from which space-time emerges. Time wouldn't be fundamental either. This is speculative, but it shows how much mystery remains about time. Despite 120 years since Einstein's special relativity, time remains enigmatic. We understand time dilation, we predict and measure it, but we don't understand what time truly is at the deepest level. That's beautiful, actually. It means profound mysteries remain. Physics isn't finished. Questions still await. Puzzles remain unsolved. Insights wait to be discovered. The fact that time dilation changed our understanding completely, and that after a century we still don't fully grasp time, suggests even deeper insights await discovery. Perhaps some future physicists will achieve about time what Einstein achieved with time dilation. Perhaps they'll show time is even stranger and more wonderful than we imagine. That possibility, that the universe still holds profound mysteries, that discovery awaits. That's what makes physics exciting. That's what makes the pursuit of understanding worthwhile. There's another profound puzzle related to time dilation and black holes that physicists have grappled with for decades: the information paradox. According to classical general relativity, information falling into a black hole is lost forever. Once something crosses the event horizon, it's trapped. From a distant observer's perspective, it vanishes. But quantum mechanics says information can't be destroyed. Total information in a closed system must be conserved. This is conservation of information. These principles conflict. If information falls into a black hole and is lost, that violates quantum mechanics. If information is conserved, where does it go? Stephen Hawking's Hawking radiation discovery offered a possible resolution. If black holes emit radiation and eventually evaporate, the information they contained must be encoded in that radiation. The radiation must contain data about what fell in. But Hawking showed the radiation appears thermal, random, with no information content. It doesn't seem to encode anything about what fell in. So how can information be preserved? This is the information paradox, still unresolved. Perhaps information is encoded in subtle radiation correlations we haven't deciphered. Perhaps event horizons store information. Perhaps information itself needs reconceptualization in quantum gravity contexts. The paradox connects to time dilation and causality deeply. It involves quantum mechanics at extreme space-time curvature, involving such extreme time dilation effects that current understanding breaks down. This raises fundamental questions. Is causality preserved in quantum gravity? Can information travel backward in time? Can causality be violated? In 1992, physicist Igor Novikov proposed the Novikov self-consistency principle. It states if time travel existed, the past would be fixed, unchangeable. Any attempt to change the past would be prevented by physical law. Events would conspire towards self-consistency. If you traveled back to kill your grandfather, something would prevent you. Your gun might jam. You'd get sick. The universe would arrange events so the grandfather survived, because he did in actual history. This preserves causality without forbidding closed, time-like curves. Time travel could exist, but you couldn't change history. Others propose Hawking's chronology protection conjecture. The laws of physics prevent time travel. Though closed time-like curves don't mathematically violate Einstein's equations, nature might prevent them through unknown mechanisms, perhaps quantum effects, perhaps undiscovered principles. These ideas remain speculative. We don't know if closed time-like curves are possible or if nature permits time travel. But considering these questions illuminates deep aspects of causality, time, and space-time structure. Time dilation opens questions we're still exploring. It connects to physics' deepest mysteries: black holes' nature, quantum gravity, time's arrow, causality, and information preservation. Understanding time dilation, that time is flexible and relative, is a first step toward deeper mysteries. And that journey, that pursuit of understanding, is one of humanity's noblest activities. I think about what time's relativity means, what it means that time passes at different rates in different places, what it means that time is woven into space-time, intertwined with space and gravity. It means the universe is far stranger, far more wonderful, far more worthy of awe and curiosity than everyday intuition suggests. It means that through careful observation and deep thinking, following mathematics where it leads, we uncover truths that would seem impossible before discovery. It means the universe still holds secrets. It means profound questions remain. Deep mysteries await exploration. Wonders wait to be discovered. Let me add context I haven't fully covered. Time dilation isn't the only strange effect from relativity. It's one of several interconnected phenomena flowing from the same principles. When something moves at high speed, not only does time slow down, so does length contract. This is length contraction. An object moving at 99.9% light speed appears about 22 times shorter in its motion direction than at rest. This doesn't violate length conservation. From the moving object's perspective, lengths around it contract instead. Relativity is consistent. Different observers measure different things, but all find the same physical laws apply. There's also relativistic mass increase. As an object moves faster, its inertia increases, harder to accelerate further. This is described as momentum and energy increase in modern physics rather than mass change. These effects, time dilation, length contraction, relativistic mass, are different aspects of the same reality. Space-time differs from intuition. Moving at high speeds or in strong gravity produces seemingly impossible effects but are completely consistent with mathematics and observations. Einstein recognized these effects follow from a fundamental principle. Light speed is constant and maximum. Nothing exceeds it. This principle, combined with requiring physical law consistency for all observers, necessarily produces these strange effects. It's remarkable how strange and wonderful this is. Before Einstein, physicists thought space and time were absolute. Everyone agreed on distances and intervals. Einstein showed this is wrong at high speeds and strong gravities. Space and time are flexible, they're intertwined, they're relative. This isn't just theory. We observe these effects. We measure them. GPS wouldn't work without time dilation. Particle accelerators wouldn't work without relativistic effects. Stars and galaxies behave according to relativistic predictions. Yet, there's something miraculous about it. From a simple principle, light speed's constancy, a cascade of consequences flows. Time dilation, length contraction, simultaneity's relativity, mass energy equivalence, space-time curvature, black holes. Each follows inevitably from the basic principle. Each has been confirmed by observation. Each reveals reality is more interconnected, more unified, more beautiful than imaginable. This draws people to physics. Not just understanding how things work, but discovering reality has deep elegance. That simple principles lead to profound consequences, that the universe has hidden structures revealed through thought, mathematics, and careful observation. When I contemplate time dilation, I'm struck by this elegance, that something so profound, that time isn't absolute, emerges from something so simple that light speed is constant everywhere, that physicists, thinking carefully about what constancy of light speed means, derive through pure mathematics that time must be relative. That subsequent observations confirm this radical idea, that now it's woven into every technology we depend on. This is the scientific method at its best. Careful thought, mathematical reasoning, experimental confirmation. Truth emerges. Understanding deepens. The universe reveals itself to be stranger, more wonderful, more interconnected than we imagined. To truly understand time dilation, work through thought experiments. These hypothetical scenarios build intuition. Consider the light clock thought experiment. Imagine a clock made of two mirrors separated by a distance with light bouncing between them. Each round trip is one tick. In a moving spaceship from inside, light travels perpendicular to motion direction. From Earth's perspective, watching the spaceship pass, light travels diagonally. From Earth's perspective, light must travel farther. Since light speed is constant, longer distance means longer time. So the Earth observer sees the clock tick slower. This is time dilation. The moving clock genuinely runs slower from the stationary observer's perspective. It's not an illusion. Physicists use spacetime diagrams to visualize relativity. These graphs show space on one axis, time on the other. A point represents a location at a time. A vertical line represents an at-rest object. Time changes, position doesn't. A diagonal line represents movement. Both position and time change. In space-time diagrams, the light clock example can be drawn. The moving clock's path appears different from a stationary clock's path. The geometry makes clear why time passes differently. These diagrams are powerful. They show time and space are woven together. A motion change is literally space-time rotation, mixing space and time coordinates. Moving faster rotates your world line in space-time. This rotation mixes coordinates, causing time to pass slower and distances to contract. It's remarkable that space-time geometry has such concrete, observable consequences. The geometry is physics. The math predicts reality. Another thought experiment, the twin paradox, thought through carefully. Twins Alice and Bob. Alice flies away at near light speed. Bob stays on Earth. Time dilation makes Alice age slower. When Alice returns, she's younger. This seems impossible. From Alice's perspective, Bob was moving, so Bob should age slower. From Alice's perspective, she should be older. The resolution. The situation isn't symmetric. Alice experiences acceleration when turning around. Alice changes velocity. Bob doesn't. This asymmetry breaks symmetry in the situation. Alice's clock genuinely runs slower overall. When you account for acceleration carefully, work through physics properly, Alice is younger. This is an illusion. It's real. Astronauts on the ISS age slightly slower than Earth people. The effect is tiny but measurable. These thought experiments build time dilation intuition. They show mathematics is consistent. They show time truly is relative. They show relativity makes predictions matching observations. Working through these examples, something becomes clear. Time dilation isn't magic. It's not incomprehensible. It follows necessarily from the principles of relativity. Once you understand that light speed is constant and that physical laws must be the same for all observers, Time dilation follows inevitably. It's like geometry. Once you accept the axioms of Euclidean geometry, countless theorems follow necessarily. Similarly, once you accept light speed constancy, time dilation and other relativistic effects follow mathematically. The universe has a logical structure. Understanding one part helps understand others. Truth has an elegance and consistency to it, and that consistency, that elegance, is one of the most beautiful things about physics. It means the universe isn't arbitrary, it's not random, it follows deep, beautiful, interconnected principles. We can understand it through thought and mathematics. And that understanding, that glimpse into the universe's deep structure, is profoundly beautiful. Let me explore how time dilation affects our understanding at cosmic scales. Relativity provides the framework for cosmology, studying the universe's large-scale structure and evolution. Einstein's general relativity describes how space-time curves due to mass and energy. On cosmic scales, this curvature determines how the universe expands. When Einstein first applied general relativity to cosmology, he found something troubling. Equations predicted the universe should either collapse or expand indefinitely. It couldn't be static. But in the early 1900s, the prevailing idea was that the universe was eternal and unchanging. So Einstein added a cosmological constant term to force a static solution. Later, when Hubble discovered galaxies moving apart and the universe expanding, Einstein called the cosmological constant his greatest blunder. But time has vindicated it. In 1998, astronomers discovered the universe isn't just expanding, it's accelerating. Something pushes galaxies apart faster and faster. This is dark energy, behaving, exactly like Einstein's cosmological constant. Time dilation is crucial for understanding this. In an expanding universe, observers at different locations experience different time passage rates. The universe's expansion is described by a metric, the Friedmann-Lemaitre-Robertson-Walker metric, determining how time flows. This metric shows observers at different cosmic distances experience time at different rates relative to each other. As the universe expands, the time-distance relationship changes. Distant galaxies appear to age differently from nearby galaxies in a sense. The accelerating expansion driven by dark energy has profound fate implications. If expansion continues accelerating indefinitely, the universe faces heat death scenario. Eventually, all stars will burn out. All matter will decay. The universe will expand to infinite volume and zero density and zero temperature. Hawking radiation from black holes will cause evaporation over cosmic timescales. Even protons might decay, though we've never observed this. Eventually, only radiation and elementary particles will remain, infinitely dispersed in an infinitely large, infinitely cold universe. This fate is a direct consequence of relativistic cosmology. It emerges from applying Einstein's equations to the universe as a whole. It's a prediction made by understanding space-time on cosmic scales. This brings us back to time. As the universe expands and cools and dilutes, how does time pass? According to relativity, time is tied to space-time structure. As space-time evolves, so does time's nature. In the infinitely distant future of an eternally expanding universe, time might lose all meaning. There will be no changes, no events, no motion. Time might become meaningless because nothing will happen anymore. Or perhaps quantum mechanics will prevent this infinite future. Perhaps something we don't understand will happen. But according to our current understanding, the universe faces a cold, dark, infinitely distant eternity. This is a profound consequence of understanding time dilation, and relativity. It's not just about clocks running at different rates or astronauts aging slowly. It's about understanding the universe's structure, evolution, and ultimate fate. It's about realizing we live in a cosmos governed by deep, interconnected principles. Understanding these cosmic implications makes time dilation even more profound. And it makes us realize something remarkable. We live during the universe's youth. While stars shine, planets exist, life is possible. This period, a mere blink in cosmic time, is when the universe is alive with activity. Eventually, hundreds of trillions of years from now, the universe will be cold and empty. But for now, here, in this cosmic instant, the universe brims with possibility. Stars are forming. Galaxies are evolving. On at least one planet, life has emerged and developed enough to understand time dilation and contemplate the universe's fate. That we can understand something so profound that we can peer into the future billions of years hence through the lens of relativity is remarkable. It's one of humanity's greatest achievements. Understanding time is understanding ourselves and our place in the cosmos. Let me address some common misconceptions about time dilation. First, time dilation is an illusion, or just how we measure things. This is wrong. A clock on a fast-moving spaceship genuinely runs slower. If you traveled at high speed for 1 year and returned to Earth, you'd have aged 1 year, but 50 years might have passed on Earth. This isn't measurement, it's actual physical aging. Second, time dilation only matters at extremely high speeds. Partly true, but misleading. The effects are tiny at ordinary speeds, but tiny isn't absent. Atomic clocks on airplanes show measurable time dilation. GPS satellites wouldn't work without accounting for it. Particle accelerators wouldn't function without it. The effects are real even when small. Third, special and general relativity are separate. They're related. Special relativity describes time dilation from motion. General relativity describes time dilation from gravity, but they're part of a unified framework. Motion and gravity affect spacetime similarly, but differently. Fourth, light speed constancy violates conservation laws. It doesn't. All conservation laws hold. Energy, momentum, angular momentum, all conserved. The formulas look different because relativistic energy includes mass energy. Relativistic momentum includes the Lorentz factor. Conservation laws hold. Fifth, time travel is possible in relativity. This is unproven. General relativity mathematically allows closed time-like curves in principle, but whether they can exist, whether quantum mechanics prevents them, whether they're realizable, these are open. Don't assume time travel is real from relativity alone. Sixth, all reference frames are equally valid. Special relativity says all inertial frames, non-accelerating, are equally valid. But accelerated frames are different. Black hole event horizons define special frames. Cosmic expansion selects a special frame. While relativity is relative, it's not true that anything goes. Understanding these misconceptions clarifies what time dilation actually is. It's not magic. It's not mysterious as unexplainable. It follows from consistent principles. Observation has confirmed it thousands of times. What makes it seem mysterious is that it violates everyday intuition. We don't experience time dilation daily. Intuition evolved for low speeds and weak gravity. In that regime, time appears absolute. But intuition doesn't capture how the universe actually works. This is common in physics. Quantum mechanics is counterintuitive. Thermodynamics seems to violate intuition until you understand entropy. Relativity violates time intuition. But beneath the counterintuitive surface is deep consistency. The universe follows laws. Laws are encoded in mathematics. Mathematics is reliable. Following mathematics, we discover truths intuition never would have suggested. When tested, those truths match observations perfectly. This makes science powerful. It's not about intuition, not about authority or tradition. It's about observation, mathematics, and logic. Follow those three and reality reveals itself. Time dilation is perfect example. Nobody would have guessed time isn't absolute. But following the logic of constant light speed and consistent physical laws, Einstein derived that time must be relative. An observation confirmed it. That's the power of scientific understanding. We can know things that seem impossible, that seem to violate basic intuition, because we can test them, measure them, confirm them through careful observation. This is how knowledge progresses. This is how we understand the universe. And time dilation, this strange and wonderful phenomenon, is one of the jewels of human understanding. It shows that reality is more profound, more interconnected, more beautiful than everyday experience suggests. Let me talk about something crucial to understanding relativity: the observer's role. Relativity is often misunderstood as saying everything is relative, or everything depends on your perspective. This is misleading. In relativity, observers in different reference frames, different motion states, measure different things. An Earth observer measures different times than a spaceship observer. An observer in strong gravity measures different times than in weak gravity. These differences are real, not illusions. But this doesn't mean everything is subjective or arbitrary. Objective facts exist that all observers agree on. Light speed is one. Space-time structure is another. Physical laws are another. What varies between observers is measurements like time and distance. But behind these varying measurements is unified space-time structure, the same for all observers. Different observers slice through space-time differently, leading to different measurements, but they're describing the same underlying reality. An analogy: imagine a 3D globe. Two observers at different locations measure angles and distances differently, depending on their position and orientation. But there's an underlying objective 3D sphere both observers measure. They're not disagreeing about the sphere's existence or structure. They're measuring it from different angles. Similarly, in space-time, different observers measure time and space differently due to their motion and gravitational field location. But they're measuring the same underlying space-time structure. The mathematics of space-time, the metric describing how to measure distances and time intervals, is objective and the same for all observers. This is why general relativity is so powerful. It provides a unified space-time description encompassing all observers, all reference frames, all possible motions, and gravitational fields. Equations are the same whether you're in an inertial or accelerated frame, in weak or strong gravity. The fact that different observers measure different times is a feature, not a bug. It's a consequence of space-time being unified. Time and space are woven together. How you slice through the time-space fabric depends on your motion and location. Different slices give different time and space measurements. This is profoundly beautiful. It means the universe has deep unity. All observers, despite measuring different numbers, observe the same objective reality described by the same objective laws. Relativity is about finding deep unity beneath different measurements. Understanding this helps understand why time dilation is real, but different observers measure different amounts. An Earth observer measures that time runs slower on a spaceship. A spaceship observer measures that time runs slower on Earth. Both are correct in their reference frames. They're not contradicting, they're describing different space-time slices. The resolution comes from carefully tracking what each observer measures and applying transformation laws relating different reference frames. When done correctly, everything is consistent. No contradictions exist, just different observers measuring different things because they're in different motion states. This is why relativity required thinking revolution. We had to learn thinking in space-time terms rather than separate space and time. We had to learn measurements depend on observers. We had to learn this doesn't mean reality is subjective, but that reality has structure encompassing all observers. It's abstract thinking. It requires carefully following mathematics, but it's worth it because the payoff is reality description that's consistent, beautiful, and observation confirmed. This understanding that observers can measure different things while describing the same underlying reality is perhaps the deepest insight of relativity. It shows that reality has unity beneath apparent diversity. It shows that science is about finding universal truths that all observers can agree on, even when they measure different values. There's an object in space that's so dense, so gravitationally powerful that nothing can escape from it. Not matter, not light, not even information itself, some argue. It's so strange that for decades, physicists weren't sure it could actually exist. It violated intuition so profoundly that even Einstein wasn't convinced. But it's real. And it's one of the most fascinating and terrifying objects in the universe. A black hole. The idea of a black hole starts with a simple question. What happens if you compress something down really small? If you take an object and squeeze it, squeeze it, squeeze it until it becomes infinitely dense, what would happen? Gravity is the force that pulls things together. The more massive something is, and the closer you are to it, the stronger gravity is. If you compressed an object into a tiny space, you'd increase its density enormously. The gravity would become incredibly strong. There's a theoretical point called the event horizon. This is a boundary around an object where the escape velocity, the speed needed to escape that object's gravity, equals the speed of light. If the object is compressed inside its event horizon, then nothing can escape, not even light. It's a black hole. The size of the event horizon depends on the object's mass. For an object with the mass of Earth, the event horizon would be about 9 millimeters. For an object with the mass of the Sun, it would be about 3 kilometers. For a supermassive black hole with the mass of millions of suns, it could be millions of kilometers across. But here's the thing, this is all theoretical. We're talking about objects so extreme that they require compressing matter to densities never observed in nature. Except they do exist. We've found them. We've observed them. The first person to calculate what a black hole would be like was Carl Schwarzschild in 1916. He solved Einstein's field equations and found a solution describing a spherical black hole. The boundary of this black hole, the event horizon, is called the Schwarzschild radius. But for a long time, physicists thought these were just mathematical curiosities. They didn't think black holes could actually form in nature. It seemed too extreme, too impossible. Then, in the 1960s, physicists, including Roy Kerr, discovered solutions describing rotating black holes. And other physicists realized that black holes could form when massive stars explode as supernovae. If the remaining core is massive enough, It could collapse and become a black hole. So black holes went from theoretical curiosities to plausible objects that could exist in the universe. And then, in the 1970s, Stephen Hawking made a shocking discovery. Black holes aren't completely black. They emit radiation. This is called Hawking radiation, and it means black holes can eventually evaporate. This discovery was profound because it connected black holes to thermodynamics. Black holes have temperature. Black holes have entropy. Black holes are subject to the laws of thermodynamics. Since then, black holes have become central to theoretical physics. They're laboratories for testing our theories. They're places where general relativity and quantum mechanics come together. They're fascinating objects worthy of study in their own right. And we've actually observed them. In the past few decades, astronomers have found evidence of black holes throughout the universe. Small black holes formed from collapsed stars, supermassive black holes at the centers of galaxies, black holes colliding and merging, sending out ripples in spacetime called gravitational waves. The observation of black holes has opened up an entire new window on the universe. We can study them using telescopes. We can detect their effects on nearby matter. We can even observe gravitational waves from merging black holes. And the more we learn about black holes, the more fascinating they become. They challenge our understanding of physics. They raise deep questions about the nature of space, time, and information. They hint at physics we don't yet understand. So what is a black hole, really? What happens inside? How do they form? How do we observe them? And what do they mean for our understanding of the universe? Let me start by explaining what happens at the event horizon. The event horizon is not a physical barrier. It's not a surface you can touch or feel. It's a mathematical boundary defined by properties of spacetime. It's the point of no return. If you're inside the event horizon traveling toward the black hole's center, you cannot escape. All paths lead inward. You cannot travel outward faster than the speed of light, and light itself cannot escape, so nothing can escape. But something strange happens at the event horizon from the perspective of distant observers. As you fall toward the event horizon, from the distant observer's perspective, you appear to slow down. Your clock appears to run slower and slower. Your image appears to fade and redshift. From the distant observer's perspective, you would take infinite time to reach the event horizon. You would appear frozen at the horizon. Your image redshifted to invisibility. This is a direct consequence of time dilation near a black hole. Time runs so much slower near the event horizon that, to a distant observer, time appears to stop entirely at the event horizon itself. But from your own perspective, if you were falling into the black hole, you wouldn't notice anything special at the event horizon. Time would pass normally for you. You would cross the event horizon in finite time. You might not even notice the moment you cross if the black hole is large enough that tidal forces are gentle. You'd cross the event horizon without realizing it and then continue falling toward the singularity. This asymmetry between what a distant observer sees and what a falling observer experiences is one of the most profound consequences of general relativity. Two observers in different space-time locations measure drastically different things. The event horizon is a boundary that means something very different depending on your perspective. The event horizon itself is defined mathematically by the Schwarzschild metric, the solution to Einstein's equations for a non-rotating black hole. For a black hole of mass m, the Schwarzschild radius is r sub s equals 2, gm over c squared, where g is Newton's gravitational constant and c is the speed of light. This simple formula gives the size of the event horizon in terms of the black hole's mass. For a 1 solar mass black hole, r sub s is about 3 kilometers. For Earth's mass, r sub s is about 9 millimeters. For a supermassive black hole of 4 million solar masses, r sub s is about 12 million kilometers, about 80 times the distance from Earth to the Sun. The interesting thing about the Schwarzschild radius is how it scales with mass. A more massive black hole has a larger event horizon, but it also has weaker gravity at the event horizon. A supermassive black hole with an event horizon the size of our solar system might have tidal forces at the horizon gentle enough that you could cross it without noticing, whereas a stellar black hole with an event horizon just a few kilometers across would have such extreme tidal forces that you'd be torn apart well before reaching the horizon. For a rotating black hole, described by the Kerr metric, the situation is more complex. A rotating black hole has not one, but two event horizons, the outer event horizon and the inner Cauchy horizon. Between these two horizons is a region called the ergosphere, where spacetime itself is dragged around by the black hole's rotation. In the ergosphere, you cannot stand still. No matter how powerful your spaceship's engines are, you cannot hover at a fixed position. You must orbit with the black hole's rotation. This is called frame dragging, and it's a direct consequence of how rotation warps spacetime. If you could somehow cross the Cauchy horizon, though it would likely be unstable and destroyed by quantum effects, you'd enter a region of spacetime called the inner black hole region, where unusual things might happen. But this is highly theoretical and speculative. Most real black holes we observe are probably rotating to some degree. Earth rotates. Stars rotate. When a star collapses to form a black hole, angular momentum is conserved, so the black hole should rotate. The more rotating a black hole is, the more extreme the ergosphere becomes. This asymmetry between what a distant observer sees and what the falling observer experiences is one of the most profound consequences of general relativity applied to black holes. Once you cross the event horizon, you're doomed. You're going to hit the singularity eventually. The singularity is the infinitely dense center of the black hole, where all the mass is concentrated. At the singularity, space-time curvature becomes infinite. Our current understanding of physics breaks down. We don't know what happens at the singularity. Quantum gravity, a theory combining quantum mechanics and general relativity, might describe what happens, but we don't yet have a complete theory of quantum gravity. Between the event horizon and the singularity, there's a region called the black hole's interior. In this region, all paths lead toward the singularity. The singularity is in the future. You cannot avoid it any more than you can avoid the future in normal space-time. This is a profound idea. Inside a black hole, the singularity isn't in a particular location. It's in the future. All time-like paths lead toward it. You cannot escape it because you cannot escape the future. Now, how do black holes form? The most straightforward way is through stellar collapse. When a massive star, roughly 20 times the mass of the Sun or more, runs out of fuel, it can no longer support itself against its own gravity. The core collapses catastrophically. If the core is massive enough, nothing can stop the collapse. Electrons get pushed into protons, forming neutrons. But neutrons themselves can't support the weight. The collapse continues. The matter becomes compressed to infinity density. The event horizon forms around this collapsing matter, and a black hole is born. For many years, astronomers searched for evidence of black holes. They looked for objects with masses too large to be anything else. They looked for X-rays from material falling into black holes. They looked for effects on nearby stars orbiting black holes. And they found them. The first confirmed black hole was Cygnus X1. Discovered in the 1970s, it's a black hole orbiting a blue supergiant star. Material from the star flows toward the black hole, heats up, and emits X-rays. Since then, hundreds of black holes have been discovered. We found small stellar mass black holes and supermassive black holes at the centers of galaxies. In 2019, we got the first direct image of a black hole's shadow at the center of the galaxy, M87. This image was remarkable. It showed the shadow of the black hole, the region from which no light escapes, surrounded by a glowing ring of material. It was direct visual evidence that black holes are real. And in 2022, we got an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy. This black hole has a mass of about 4 million suns. Its event horizon is about 12 million kilometers across. These images are profound. They show that black holes exist. They confirm Einstein's predictions about space-time curvature. They open up the possibility of studying black holes in unprecedented detail. Black holes also connect to gravitational waves. When two black holes orbit each other and eventually merge, they send out ripples in space-time, gravitational waves. These waves were detected directly in 2015 by the LIGO Gravitational Wave Observatory. This detection confirmed another prediction of general relativity. It opened up a new way to observe the universe. Now we can detect gravitational waves from merging black holes, colliding neutron stars, and other cataclysmic events. Black holes are laboratories for extreme physics. They're places where gravity is so strong that relativistic effects dominate. They're places where quantum effects might become important. They're gateways to understanding physics at the deepest level, and they're still mysterious. We don't fully understand what happens at the singularity. We don't understand how information behaves inside a black hole. We don't understand whether naked singularities, singularities not surrounded by event horizons, can exist. But the study of black holes has profound implications for physics and philosophy. It shows that the universe is stranger, more extreme, more wonderful than we could have imagined. Now let me go deeper into some of the most fascinating aspects of black holes that I haven't fully covered. First, Hawking radiation and black hole thermodynamics. In 1974, Stephen Hawking made a discovery that shocked the physics community. Black holes aren't actually black. They emit radiation. For decades before Hawking's work, physicists thought black holes were perfectly black. They absorbed everything and emitted nothing. But Hawking showed that quantum mechanical effects near the event horizon can cause black holes to emit radiation. The mechanism is remarkable. Quantum mechanics allows virtual particle-antiparticle pairs to constantly appear and disappear from the vacuum. These are quantum fluctuations allowed by the uncertainty principle. Near the event horizon of a black hole, something extraordinary happens. One member of a pair can fall into the black hole while the other escapes. To a distant observer, it appears that a real particle has been emitted from the black hole. This is Hawking radiation. The black hole has lost energy, the energy of the escaped particle, so the black hole's mass decreases. Over cosmic timescales, a black hole can completely evaporate by emitting Hawking radiation. The temperature of Hawking radiation is inversely proportional to the black hole's mass. Smaller black holes are hotter. A stellar mass black hole would have a temperature around a millionth of a degree above absolute zero, colder than the cosmic microwave background that fills space. Such a black hole would emit radiation so slowly that it would take longer than the current age of the universe to lose a significant fraction of its mass. But a small black hole with the mass of a mountain would have a much higher temperature and would emit radiation more rapidly. If you could somehow collect Hawking radiation from such a black hole, you'd detect real particles coming out. The smallest possible black holes, formed in the early universe before stars existed, might have evaporated completely by now through Hawking radiation. Primordial black holes, if they exist, would emit radiation violently as they approach complete evaporation. Hawking radiation is fundamentally connected to thermodynamics. Black holes have temperature, they have entropy. Jacob Bekenstein showed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This was shocking because it violated intuitions about entropy and about the nature of black holes. The entropy formula is S equals A times K times C cubed over 4 times G times H bar, where A is the event horizon area, K is Boltzmann's constant, C is light speed, G is Newton's constant, and H bar is Planck's constant. This formula has profound implications. It suggests that black hole entropy, which should measure information content, is related to surface area, not volume. This is weird and counterintuitive. It hinted that information in a black hole might be encoded on its event horizon, like information on a hologram. This led to the holographic principle, the idea that all information in a volume of space can be encoded on its boundary surface. It's one of the most profound ideas in theoretical physics, and black hole thermodynamics was crucial to developing it. Now, one of the deepest puzzles in physics is the black hole information paradox. If information falls into a black hole and the black hole eventually evaporates through Hawking radiation, what happens to the information? Is it destroyed? Does it escape in the radiation? Or does the universe prevent information from ever entering a black hole? This paradox sits at the intersection of quantum mechanics, thermodynamics, and general relativity. In quantum mechanics, information can never be completely destroyed. The universe must preserve information. But if information falls into a black hole and the black hole evaporates, the information appears to be destroyed. This is a profound problem because it suggests that either 1, quantum mechanics is wrong in some regime, 2, information escapes in Hawking radiation, but encoded in a way we don't understand, or 3, black holes don't actually completely evaporate, preserving information in a remnant. Various solutions have been proposed. Some physicists argue that information is subtly encoded in correlations in Hawking radiation that we haven't figured out how to decode. Others argue that quantum gravity modifies Hawking radiation in ways that preserve information. Still others argue that information somehow remains preserved at a black hole remnant with Planck scale mass. The information paradox remains one of the deepest unsolved problems in theoretical physics. Understanding it might require a complete theory of quantum gravity, something physicists are still searching for. Black holes also connect interestingly to time travel and causality. Near a black hole, spacetime is so warped that closed time-like curves, pass through spacetime that loop back to earlier times, might be possible. However, the laws of physics seem to conspire to prevent actual time travel. The cosmic censorship conjecture proposed by Roger Penrose states that singularities are always hidden inside event horizons. If true, this would prevent naked singularities that might allow time travel. Another consideration: while rotating black holes mathematically allow paths that could lead to the past through the inner Cauchy horizon, these regions are likely unstable due to quantum effects. Anything falling through the Cauchy horizon would be destroyed by quantum fluctuations. So practical time travel through black holes seems impossible. Black holes come in different sizes and types. Stellar mass black holes form from collapsed stars. These typically range from a few solar masses to perhaps 20 solar masses, though the exact upper limit isn't known. These are relatively small objects, a few kilometers across, with extreme gravity and tidal forces. Intermediate mass black holes have been recently discovered. These have masses in the hundreds or thousands of solar masses. Their origin is still debated. They might form from mergers of stellar mass black holes, or they might form differently in dense star clusters. Supermassive black holes have millions to billions of solar masses. These sit at the centers of galaxies. Nearly every large galaxy seems to have a supermassive black hole at its center. The supermassive black hole in our own galaxy, Sagittarius A star, has a mass of about 4 million suns. It's unclear how supermassive black holes formed. They might have grown from smaller black holes through mergers and accretion, or they might have formed directly from the collapse of massive gas clouds in the early universe. We don't yet know. Observing black holes has become an increasingly sophisticated art. For decades, astronomers could only infer black holes' existence from their effects on nearby matter. A black hole orbiting a star would pull material from the star, creating an accretion disk. This material would heat up and emit X-rays. Cygnus X1 was the first confirmed black hole discovered in the 1970s through X-ray observations. It's a stellar mass black hole in an X-ray binary system, a black hole orbiting a blue supergiant star. Material flows from the star toward the black hole, forming an accretion disk that reaches millions of degrees and emits intense X-rays. In more recent decades, astronomers have observed supermassive black holes by watching stars orbit them. At the center of our galaxy, stars orbit Sagittarius, a star with periods of 15 to 20 years. By measuring their orbits over decades, astronomers can calculate the mass of the central black hole. The orbital measurements conclusively show a black hole with 4 million solar masses. But the most recent breakthrough is direct imaging of black holes. In 2019, the Event Horizon Telescope, a network of radio telescopes around the world, produced the first direct image of a black hole. The image showed the shadow of the black hole at the center of galaxy M87, surrounded by a glowing ring of material. This image was profound. It directly showed the event horizon's edge. It confirmed Einstein's predictions about how light bends around black holes. It opened a new era in black hole observational astronomy. Then, in 2022, the same team imaged Sagittarius A star, the supermassive black hole at our galaxy's center. Despite being closer to Earth, Sagittarius star was harder to image because it's smaller and less active than M87's black hole. These images represent one of the greatest achievements in observational astronomy. They required coordinating radio telescopes across the globe using interferometry to create a virtual telescope the size of Earth. The data analysis required years of work and advanced computational techniques. Gravitational waves from black holes offer another window for observation. When two black holes orbit each other and merge, they emit gravitational waves, ripples in spacetime itself. These waves were detected directly in 2015 by LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO detected gravitational waves from two stellar mass black holes merging billions of light years away. The signal lasted a fraction of a second, but it was unmistakable. It confirmed that gravitational waves are real and opened a new era of gravitational wave astronomy. Since then, dozens of black hole mergers have been detected through gravitational waves. Each detection teaches us about black hole masses, spins, and formation mechanisms. Gravitational wave detections have discovered black holes more massive than expected and revealed populations of black holes we didn't know existed. Let me discuss accretion disks and X-ray binaries in more detail, because this is how we've observed many black holes and learned much about their properties. When a black hole has a companion star nearby, it can pull material from that star. This material doesn't fall straight into the black hole. Instead, it forms a rotating disk around the black hole, called an accretion disk. Why a disk? Because of angular momentum. Material falling toward the black hole has some angular momentum from the star's orbit. Instead of falling straight in, this material spirals inward in a disk, like water spiraling down a drain. In an accretion disk, material collides and friction heats it to extremely high temperatures. Close to the black hole, material can reach temperatures of millions of degrees. At these temperatures, material emits intense X-rays. This is how black holes were first observed. Astronomers looked for X-ray sources in the sky and found some that seemed to be associated with visible stars. The X-rays were coming from material falling into black holes. Cygnus X1 was the first confirmed black hole, discovered through X-ray observations in the 1970s. It's a stellar mass black hole with a mass of about 15 solar masses orbiting a massive blue supergiant star called HDE 226868. Material flows from the star toward the black hole, forming an accretion disk. This disk heats up to millions of degrees and emits intense X-rays. From Earth, we see both the visible light from the star and the X-rays from the accretion disk. By measuring the orbital period and the star's motion, astronomers could calculate the black hole's mass. The calculations showed the companion object had to be more massive than any known neutron star could be. It had to be a black hole. Since then, many more black holes have been discovered in X-ray binary systems. These systems show fascinating behavior. Sometimes the accretion is steady, producing constant X-rays. Other times it's variable, producing sudden bursts of X-rays called outbursts. The outbursts are thought to result from thermal instability in the accretion disk. When the disk cools to a certain temperature, it becomes less ionized. This reduces friction, causing the disk to contract. The contraction heats the disk again, which ionizes it, increasing friction. This cycle repeats, producing outbursts. Another feature of accretion disks is jets. Some black holes launch jets of material at nearly the speed of light, perpendicular to the accretion disk. These jets can extend for thousands of light years and radiate intense radiation. Jets are thought to be launched by magnetic fields in the accretion disk. The rapid rotation and intense magnetic fields can channel material along magnetic field lines, launching it outward at relativistic speeds. The physics of accretion disks and jets is complex and still not fully understood, but observing these systems teaches us about black holes and their effects on surrounding material. Supermassive black holes also have accretion disks and can produce jets. The jets from active galactic nuclei, Supermassive black holes that are actively accreting material can extend for hundreds of thousands of light years and radiate enormous amounts of energy. The most powerful jets are thought to come from rapidly rotating supermassive black holes with strong magnetic fields. The Penrose process, a theoretical mechanism where energy can be extracted from a rotating black hole, might help power these jets. Understanding accretion disks and jets is important for understanding how black holes affect their environment and how galaxies evolve, because supermassive black holes and their jets can profoundly influence galactic evolution. Now let me discuss tidal forces and what happens when you fall into a black hole. If you fell toward a black hole, you'd experience tidal forces, differences in gravitational pull across your body. Your feet would experience stronger gravity than your head, pulling them apart. These are called spaghettification forces because they'd stretch you like spaghetti. The magnitude of tidal forces depends on the black hole's size. For a stellar mass black hole with a few solar masses, tidal forces would be extreme well before you reach the event horizon. You'd be torn apart at a distance of thousands of kilometers. But for a supermassive black hole, tidal forces at the event horizon would be relatively gentle. The event horizon of a 4 million solar mass black hole is about 12 million kilometers across. At this radius, tidal forces might be only a few times Earth's gravity. You could cross the event horizon without noticing anything. But once inside, you'd be in trouble. You'd be inexorably drawn toward the singularity. The tidal forces would increase as you got closer. And before reaching the singularity, quantum effects might become important. What would you see as you fell toward the black hole? As you approached the event horizon, you'd see the universe around you appear to change. Starlight would appear to shift toward the blue end of the spectrum. Blue shift because of your motion. The universe around you would appear to speed up. Clocks on the outside would appear to run faster from your perspective. As you cross the event horizon, the universe around you would appear to compress toward a single point behind you. You'd be fallen into a region cut off from the rest of the universe. The event horizon would appear to be a barrier from the inside, though from the outside, you'd appear to take infinite time to reach it. What happens at the singularity? Nobody knows. Quantum gravity is needed to answer this question, and we don't yet have a complete theory of quantum gravity. Some physicists speculate that the singularity isn't actually singular. Perhaps quantum gravity effects prevent the density from reaching infinity. Perhaps the singularity is replaced by something quantum mechanical but finite. Others speculate that black holes might be gateways to other universes or other regions of space-time. This is highly speculative, but it illustrates how mysterious black hole interiors remain. Now let me discuss different types and masses of black holes in more detail. Primordial black holes are black holes that might have formed in the very early universe before stars formed. They would have various masses depending on when they formed. Very small primordial black holes would have evaporated by now through Hawking radiation. Intermediate mass primordial black holes might still exist and could be observed. Stellar mass black holes form when massive stars collapse. They typically have masses between a few solar masses and perhaps 20 solar masses. The mass range is limited because of how stellar evolution works and how supernovae explode. Intermediate mass black holes have masses between a few hundred and a few million solar masses. For decades, astronomers weren't sure if intermediate mass black holes existed, but recent observations have found them, particularly in globular clusters and dwarf galaxies. Intermediate mass black holes might form through mergers of stellar mass black holes, or they might form from the collapse of massive gas clouds, or they might result from runaway collisions of stars in dense clusters. We're not sure yet. Supermassive black holes have millions to billions of solar masses. These sit at the centers of most large galaxies. Our own galaxy's central black hole, Sagittarius A star, has a mass of about 4 million suns. Supermassive black holes are thought to grow through mergers and accretion. When galaxies merge, their central black holes eventually merge. And by accreting material from the galaxy, black holes can grow. But the origin of the first supermassive black holes is still debated. In the early universe, the most distant quasars show evidence of billion solar mass black holes existing when the universe was less than 1 billion years old. Growing such massive black holes from stellar mass seeds in so little time seems difficult. Perhaps they formed directly from collapsing gas clouds, or perhaps they grew differently than we understand. Ultramassive black holes might exist in some giant elliptical galaxies. These would have masses of tens of billions of solar masses. Their existence and properties are still being studied. Each type of black hole teaches us different things. Stellar mass black holes teach us about stellar evolution and supernova physics. Supermassive black holes teach us about galaxy evolution. Intermediate mass black holes teach us about the full mass spectrum. Now let me discuss some specific famous black hole systems and what we've learned from them. Cygnus X1 is the prototypical black hole X-ray binary. It consists of a stellar mass black hole orbiting a massive blue supergiant star. The black hole pulls material from the star, creating an accretion disk that emits intense X-rays. Observations of Cygnus X1 have taught us about accretion physics, black hole jets, and black hole masses. Its properties match theoretical predictions well. GRS 1915 plus 105 is a particularly fascinating black hole X-ray binary. It shows rapid variability in X-rays, with intensity changing on timescales of seconds. It also shows relativistic jets, jets of material moving at near light speeds. Observations of GRS 1915 plus 105 have revealed how rapidly black hole accretion can change and how relativistic jets can be launched and accelerated. SS433 is one of the most exotic black hole systems. It contains a black hole or neutron star accreting from a supergiant star. It produces extremely powerful jets ejected at nearly 0.3 times the speed of light. These jets are precessing, wobbling like a gyroscope, creating a dramatic pattern in space. Observations of SS433 revealed relativistic jets and their precession, teaching us about how jets can be launched and deflected. Sagittarius A star is the supermassive black hole at our galaxy's center. For decades, astronomers observed stars orbiting it, measuring their orbits to determine the central black hole's mass. The orbital measurements conclusively showed a 4 million solar mass black hole. In 2022, the Event Horizon Telescope imaged Sagittarius A star, showing the black hole's shadow surrounded by glowing material. This was the first direct image of a supermassive black hole. M87 is a giant elliptical galaxy at the center of the Virgo galaxy cluster. It contains a supermassive black hole with a mass of about 6 billion suns. It produces enormous jets that extend hundreds of thousands of light years. In 2019, the Event Horizon Telescope imaged M87's black hole, showing the event horizon's shadow surrounded by a glowing accretion disk and jets. This was the first direct image of a black hole's event horizon. These observations of M87 reveal details about how black holes accrete material in launch jets at enormous distances. Ton 618 is the most luminous quasar known. It contains a black hole with an estimated mass of about 66 billion suns, one of the most massive known. It's so distant that we see it as it was when the universe was young, billions of years ago. The existence of such massive black holes in the early universe challenges our understanding of how black holes form and grow. Now let me discuss open questions and theoretical frontiers in black hole physics. One major question is, how do supermassive black holes form so quickly? In the early universe, within the first billion years, there are supermassive black holes with billions of solar masses. Growing such massive objects through stellar mass mergers and accretion seems to take longer than that. Possible solutions include primordial black holes formed directly from the early universe's density fluctuations, very rapid early growth through super Eddington accretion, or direct formation from collapsing gas clouds without going through stellar mass stages. Another question is, what is the relationship between black holes and galaxies? It's clear that supermassive black holes and their host galaxies co-evolve. Black hole feedback, where black holes inject energy into their surroundings through jets and radiation, can regulate star formation in galaxies. But the details of this relationship are still being worked out. How much does the black hole influence galaxy evolution? How much does the galaxy influence black hole growth? A third question concerns quantum gravity and black hole singularities. General relativity predicts singularities at black hole centers where physics breaks down, but quantum gravity effects should modify this. Understanding what actually happens at singularities requires a complete theory of quantum gravity. A fourth question is the information paradox. As discussed, if information falls into a black hole and the black hole evaporates, what happens to the information? Does quantum mechanics break down? Is information preserved somehow? This remains one of the deepest unsolved problems in theoretical physics. A fifth question concerns whether naked singularities can exist. General relativity mathematically allows singularities not surrounded by event horizons. But does nature prevent this through cosmic censorship? Cosmic censorship remains a conjecture, not proven, but widely believed. Understanding whether it's true has profound implications for physics and the nature of spacetime. These open questions show that despite centuries of progress, black holes remain mysterious and worthy of study. They're laboratories where our current theories face their hardest tests and where we expect to develop new physics. The future of black hole research promises exciting developments. More gravitational wave observatories will detect mergers with greater precision. Better telescopes will image black holes in more detail. Theoretical work will continue probing singularities and quantum gravity effects. Black holes represent one of the deepest mysteries in physics. Understanding them might unlock doors to comprehending the universe at the most fundamental level, and that makes studying black holes one of humanity's noblest scientific pursuits. Black holes show us that the universe is far stranger than everyday experience suggests. They show us places where reality itself becomes extreme and mysterious. They show us that there's still so much to discover and understand. And somehow, that's beautiful. The fact that after more than a century of relativity, after decades of observations, black holes remain enigmatic and worthy of study. That suggests the universe has depths we're still exploring. That suggests the human quest to understand can continue indefinitely. That suggests there's always more wonder to discover. Black holes are that wonder made manifest. They're cosmic mysteries that inspire awe and curiosity. They're reminders that the universe is more magnificent than we usually appreciate. Thanks for watching. They're laboratories where our theories face their ultimate tests. They're places where gravity is so strong that relativistic effects dominate completely. They're laboratories for understanding quantum gravity. Understanding black holes might be key to understanding the deepest nature of reality, how space-time works, how quantum mechanics and gravity connect, how information is preserved in the universe. The future of black hole research is exciting. More gravitational wave detectors will come online, allowing observation of black hole mergers in greater detail. Better telescopes will image black holes and their surroundings. Theoretical work will continue probing the mysteries of singularities and information. Perhaps in the coming decades, we'll develop a complete theory of quantum gravity that explains what happens at black hole singularities. Perhaps we'll solve the information paradox. Perhaps we'll discover aspects of black holes we haven't imagined yet. Black holes represent the edge of human knowledge. They're places where our understanding reaches its limits, and that makes them beautiful and worth studying. Close your eyes and think about time. Think about the past. You remember things that have happened. You remember your childhood, yesterday, this morning. You remember because those events are in the past. Now think about the future. You can imagine things that might happen. Tomorrow you might go somewhere. Next year might bring changes. You can think about possibilities, but you can't remember the future the way you remember the past. Why is there this asymmetry? Why can you remember the past but not the future? Why does time seem to flow in one direction? These are profound questions. And the answers might change how you think about reality. Because here's a radical thought. Maybe time isn't real. Maybe it's not a fundamental feature of the universe. Maybe it's something we impose on reality to make sense of it, but it's not actually there. This isn't mysticism or philosophy. This is a serious physics question. Some of the greatest physicists of the past century have grappled with it, and their conclusions are surprising. First, let's think about what we mean by time is real. We mean that time is a fundamental aspect of the universe, that there's a real distinction between past, present, and future. That time flows, that causality operates. The past causes the present, which causes the future. This is how we experience time. It feels real. It feels like time flows. It feels like there's a present moment that divides past from future. But physicists have discovered something strange. The laws of physics don't actually require this. The laws of physics are almost entirely time symmetric. They work the same running forward or backward. Throw a ball in the air, it follows a parabolic trajectory. You can describe this motion with physics equations. Now, reverse the equations. They describe the ball flying backward along the same trajectory. Both directions are equally valid according to the laws of physics. This suggests that at the level of fundamental physics, there's no arrow of time. There's no forward or backward. Time is just another dimension, like the 3 dimensions of space. This is what physicists call the block universe, or eternalism. The idea is that all of space-time, past, present, and future, exists equally. The future isn't not yet here, it's just not here, the way another location is not here. From this perspective, time isn't flowing. There's no present moment, there's just space-time containing all moments simultaneously. We experience time flowing because of how our consciousness interacts with space-time, not because time is actually flowing. This is profoundly different from our intuitive sense of time, but it follows from taking physics seriously. However, there's a major puzzle. If time is symmetric at the fundamental level, why does time seem to have a direction? Why can we remember the past but not the future? Why does entropy increase? Why do we experience time flowing? The answer lies in thermodynamics and the arrow of time, which is one of the deepest mysteries in physics. Let me explore this mystery. Let me ask, is time real? Or is it an illusion created by our limited perspective on the universe? The answer, I think, is subtle. Time might be real in some sense, but not in others. Understanding what physicists have learned about time will change how you think about reality. First, let me explain the block universe view in detail. According to this view, spacetime is a four-dimensional structure. Just as space has three dimensions, up, down, left, right, forward, back, spacetime has four dimensions, with time being the fourth. In this view, all moments of time exist equally. Your birth exists. This moment exists. Your death exists. They're all part of space-time. They're all real. The difference between them isn't that one is real and others aren't. The difference is just their location in space-time. Einstein himself held this view. He believed in what's called the Parmenidean view of space-time, after the ancient Greek philosopher Parmenides, who argued that change is illusory. Einstein once wrote, "Since there exists in this four-dimensional structure, space-time, no longer any sections which represent now objectively, the concepts of happening and becoming are not absolute, but merely relative." What does this mean? It means the now isn't universal. Different observers in different states of motion or different locations in a gravitational field disagree about which events are happening now. There's no objective present moment that's the same for all observers. This is a direct consequence of relativity. The relativity of simultaneity means that events considered simultaneous in one reference frame aren't simultaneous in another. There's no absolute now. If there's no absolute now, then the distinction between past, present, and future is observer dependent. The future, from one observer's perspective, might be the present from another observer's perspective. This led to the block universe picture. All of space-time exists. The future isn't not yet real. It's just in a different location in space-time, the way another country is in a different location in space. But this is profoundly counterintuitive. It contradicts our strong sense that there's a present moment, that now is real, that the past is gone and the future hasn't happened yet. There's an alternative view called presentism. Presentism holds that only the present exists. The past is gone. The future hasn't happened yet. Only this moment, the present, is real. Presentism matches our intuition. It explains why the present feels special. But it has problems with relativity. In relativity, there's no universal present. Different observers disagree about what's present. So what counts as the present in a presentist view? Some presentists argue that there's an objective flow of time that's just not captured by relativity. They argue that relativity is incomplete and that a deeper theory will reveal a preferred now. Others argue that presentism and relativity are compatible, but it requires accepting that our intuitions about simultaneity are wrong. What one observer calls simultaneous events happening now, another observer would say are happening at different times. A third view is called growing block universe. This view says the past and present exist, but the future doesn't exist yet. The universe grows. New moments come into being. The present is the edge of the growing block, the newest part of reality. Growing block universe combines elements of presentism, only the present and past are real, with elements of eternalism. The past persists as real, not gone. Each of these views has philosophical problems. Block universe seems to deny real change and becoming. Presentism contradicts relativity. Growing block universe requires a preferred reference frame, which also contradicts relativity. But here's the key point. None of these views are obviously wrong from physics. Physics doesn't determine which is true. Physics is compatible with all of them. This suggests that the nature of time might be as much a philosophical question as a physics question. Now, the major puzzle: if time is symmetric at the fundamental level, why does time seem to have a direction? Why can we remember the past but not the future? Why does entropy increase? Why do we experience time flowing? The answer lies in thermodynamics and the arrow of time. The arrow of time refers to the fact that time has a direction. The past is different from the future. Entropy increases toward the future. Memories point toward the past. Causes precede effects. But if the fundamental laws are time symmetric, where does this arrow come from? The answer is entropy. The second law of thermodynamics states that entropy, disorder, or the number of microscopic states consistent with a macroscopic state, increases over time. Imagine a room full of air molecules. In principle, all those molecules could spontaneously move to one corner of the room, leaving the rest empty. The laws of physics allow this, but it's fantastically unlikely. The overwhelming majority of configurations have the molecules spread throughout the room. Over time, an initial configuration with molecules concentrated in one corner will evolve toward a state with molecules spread throughout the room. Entropy increases. The process is irreversible. You don't see air molecules spontaneously concentrate in one corner. Entropy provides an arrow of time. Events with low entropy are in the past. Events with high entropy are in the future. Systems evolve from low entropy to high entropy states. This is why we can remember the past, but not the future. Memories are low entropy configurations of information in our brains. They correspond to past events. Information can flow from past events to our brains, creating memories, but information can't flow from future events because the future hasn't happened yet from our perspective. The second law of thermodynamics provides the arrow of time, the asymmetry between past and future. But here's the puzzle. Why is the initial state of the universe low entropy? Why did the universe start with low entropy and evolve toward higher entropy? This is called the problem of the initial condition. The fundamental laws don't explain it. Something about the universe's beginning, the Big Bang, resulted in low entropy. That low entropy initial condition combined with the second law of thermodynamics creates the arrow of time. Physicists like Ludwig Boltzmann grappled with this problem. He suggested that maybe the universe experiences fluctuations. In an infinitely old eternal universe, every possible state would eventually occur. Low entropy states would fluctuate into existence temporarily. Observers like us would find ourselves in the era after one of these low entropy fluctuations, experiencing time's arrow. This is called the Boltzmann brain problem and leads to bizarre conclusions, but it illustrates how deep the question of time's arrow is. Now let's think about consciousness and time. Our experience of time flowing might be intimately connected to consciousness. When you're conscious, you experience a present moment. You experience events happening. You experience the flow of time. But when you're unconscious, asleep without dreaming, You don't experience time passing. 8 hours pass but feel instantaneous to you. This suggests that time's flow might be a feature of consciousness, not a feature of the universe itself. Some physicists and philosophers argue that consciousness creates the present moment, that the act of observation, of becoming aware, creates a present moment where before there was just static space-time. This connects to quantum mechanics, where observation affects outcomes. The observer plays a special role. Perhaps the observer creates the present moment, the division between past and future. This is highly speculative, but it suggests that time's flow might emerge from how consciousness interacts with space-time, not from space-time itself. Let's think about time in relativity more deeply. Einstein showed that time is relative. Time runs at different rates for different observers depending on their motion and location in a gravitational field. This is time dilation. But relativity also shows that all moments, past, present, and future, exist on equal footing in space-time. There's no universal present. Different observers disagree about which events are in the present. This strongly suggests a block universe view. All moments exist. There's no flow of time. Time is just a dimension, like the three spatial dimensions, but relativity doesn't require this view. You could be a presentist and say that relativity just shows there's no universal present. The present is observer dependent. You could be a growing block theorist and say that the block grows at a rate determined by one's reference frame. Again, physics doesn't determine the truth. The philosophy of time must be partially philosophical. In quantum mechanics, time plays a strange role. Quantum mechanics describes how wave functions evolve over time. The Schrödinger equation tells you how a wave function changes. But here's the odd thing. The fundamental quantum processes are symmetric in time. Running them backward gives equally valid descriptions. Where does the arrow of time come from in quantum mechanics? Decoherence and measurement seem to provide an arrow. When a quantum system is measured, the wave function collapses. This collapse is irreversible. You can't uncollapse a wave function. Measurement creates an asymmetry, an arrow of time. But what counts as measurement? Does consciousness matter? This connects to the observer effect in quantum mechanics and remains mysterious. Some physicists argue that the arrow of time in quantum mechanics comes from thermodynamics, just as in classical mechanics. When you measure a system, you interact with it, creating entropy. This creates an arrow. Others argue that we don't fully understand the arrow of time in quantum mechanics. It remains an open problem. The question, is time real, ultimately connects to deep questions about the nature of reality. If all moments exist equally in space-time, is reality static without real change or becoming? Or does the flow of time come from how consciousness experiences space-time? If time is fundamental, what explains the initial low entropy condition that creates time's arrow? If time is emergent, emerging from something deeper, what is that something? These remain open questions at the frontier of physics and philosophy, and they show that despite centuries of progress, time remains one of the deepest mysteries. The experience of time is so fundamental to our existence that it's hard to question it. It's hard to imagine reality without time flowing, without a present moment, without past and future. But taking physics seriously forces us to question. The laws of physics don't require time's flow. Relativity reveals that simultaneity is relative. Thermodynamics explains the arrow of time through entropy. Quantum mechanics shows time's role is subtle and perhaps observer dependent. Time might be real in the sense that it's a genuine feature of how we experience and interact with space-time, but time might not be real in the sense of being a fundamental feature of the universe itself. Time might be emergent, arising from underlying physics. Understanding what time really is might require understanding quantum gravity, the reconciliation of quantum mechanics and general relativity. Black holes reveal that space-time can be warped and curved to extremes. Quantum effects near black holes might resolve the nature of time. So is time real? The answer is it's complicated. Time is real in how we experience it. Time's arrow is real in how systems evolve. But whether time is fundamental or emergent, whether the future truly exists or just the present, these questions remain open. And that's beautiful. It means there's still mystery. There's still so much to discover and understand about the nature of reality and our place in it. Let me go deeper into thermodynamics and the arrow of time, because this is crucial to understanding why we experience time as flowing in one direction. The second law of thermodynamics states that in an isolated system, entropy increases over time. Entropy is a measure of disorder or the number of microscopic states consistent with a macroscopic state. Imagine a cup of hot coffee sitting on a table. The coffee cools down over time. Heat flows from the hot coffee to the cooler surroundings. Eventually, the coffee and surroundings reach the same temperature. Why does the coffee cool down? In principle, the individual molecules have the same laws of motion, whether time runs forward or backward. The molecular dynamics are time symmetric, so why does heat flow from hot to cold, not from cold to hot? The answer is statistical. There are vastly more microscopic configurations corresponding to the coffee and surroundings being at the same temperature than to the coffee being hot and the surroundings being cold. When you consider all possible molecular configurations, the overwhelming majority correspond to higher entropy states. Start with a hot coffee, low entropy, and let the molecules evolve according to time-symmetric laws. Because there are so many more high entropy configurations than low entropy configurations, the system will naturally evolve toward a high entropy state, coffee cooled to room temperature. This is overwhelmingly likely, even though the laws are time symmetric. This is the key insight. Entropy increases because high entropy states vastly outnumber low entropy states. It's a statistical fact about probability, not a fundamental asymmetry in the laws. But this raises a question. Why did the universe start in a low entropy state? The Big Bang created a universe in an extremely low entropy state, a hot, dense, uniform plasma. Over time, the universe has evolved toward higher entropy. If we run the universe backward in time, it should be in a higher entropy state in the past and a lower entropy state in the future. But we observe the opposite. Entropy was low in the past and is higher now. This asymmetry, the universe having a low entropy initial condition, is called the past hypothesis. It's not explained by the laws of physics. The laws are time symmetric. The asymmetry comes from the boundary condition. The universe started in a low entropy state. Why did it? This is a profound question that physicists still debate. Some argue that quantum gravity or cosmology will eventually explain it. Some argue that it's just a brute fact about our universe. Some argue that in an eternal multiverse, universes with low entropy initial conditions are necessary for observers to exist. But regardless of the explanation, the low entropy initial condition, combined with the second law of thermodynamics, explains why we experience time flowing from past to future. It explains why entropy increases. It explains why we can remember the past but not the future. The arrow of time is essentially a thermodynamic arrow. Time's direction is determined by entropy's direction. Now let's talk about causality and determinism, because time's flow is intimately connected to causality. In our experience, causes precede effects. I decide to move my arm, and then my arm moves. The cause, decision, comes before the effect, arm movement. But in the laws of physics, causality is subtle. The fundamental equations are deterministic. Given the state of a system at one time, you can calculate its state at any other time. But they're also time symmetric. Given the state at one time, you can calculate the state at earlier or later times equally well. Causality isn't built into the fundamental equations. It emerges as a consequence of boundary conditions and entropy. Imagine a ball rolling on a table. At time 1, the ball is at position A. At time 2, it's at position B. You can say, the ball being at A causes it to be at B. But equally well, you could say, the ball being at B causes it to be at A. Causality isn't fundamental. It's how we interpret the deterministic evolution. What gives causality its direction? Entropy. Low entropy past states cause high entropy future states, not vice versa. Causality flows from past to future because entropy flows from past to future. This suggests something profound. Causality itself might be emergent, arising from entropy and thermodynamics, not fundamental. In quantum mechanics, causality becomes even more mysterious. Quantum events are probabilistic, not deterministic. An electron decays into other particles, but we can't predict exactly when or in which direction. If events are probabilistic, does causality hold? Some interpret the probabilistic nature as fundamental indeterminism. The future genuinely isn't determined by the past. Others interpret it as reflecting our incomplete knowledge. The future is determined, but we can't know it. Either way, quantum mechanics challenges the simple notion that causes determine effects. Now let's discuss historical perspectives on time, because great physicists have thought deeply about this. Isaac Newton treated time as absolute and universal. Time flows at the same rate for all observers everywhere in the universe. This fit well with Newtonian mechanics and was the accepted view for 2 centuries. But Newton himself questioned this. He wrote that absolute time flows equably without regard to anything external, suggesting he recognized the peculiarity of positing something that's unobservable and universal. In the 1800s, Ludwig Boltzmann grappled with the arrow of time. He saw that entropy increasing was a statistical consequence of starting from a low entropy state and letting probability work its magic. He recognized that this explained time's asymmetry without requiring fundamental asymmetry in the laws. Boltzmann also speculated about the Boltzmann brain problem. In an infinitely old universe with fluctuations, unlikely configurations could spontaneously form. Observers' argument remains influential in philosophy and suggests that time as we conceive it might not be real. Kurt Gödel discovered rotating solutions to Einstein's field equations that allow closed time-like curves, paths through spacetime that loop back to earlier times. This showed that general relativity permits time travel in principle, though probably not in practice. John Wheeler and Bryce DeWitt developed the Wheeler-DeWitt equation in quantum cosmology. This equation describes how the entire universe evolves. Remarkably, it has no time variable. It describes the universe as a static, timeless whole. This suggested that time might not be fundamental but emergent from quantum gravity. These historical developments show that physicists have long questioned the reality of time. The question, is time real, has deep roots in physics. Now let's discuss some specific time paradoxes and puzzles. The grandfather paradox. If you could travel to the past and kill your grandfather before your parent was born, you'd prevent your own birth. But then you couldn't travel to the past. This is a logical contradiction. Various resolutions have been proposed. The Novikov self-consistency principle says the past is fixed. You can't change it. You can travel to the past, but anything you try to do is already part of history and doesn't change anything. The many worlds interpretation says you create an alternate timeline. You kill your grandfather in that timeline, but you came from a different timeline where he lived. Killing your grandfather seems unlikely, but it illustrates how time travel creates logical puzzles. The predestination paradox involves events that seem to violate causality. You travel to the past to prevent something from happening, but your actions ensure it happens anyway. Cause and effect loop in strange ways. The ontological paradox involves creating information from nowhere. You receive a symphony from your future self, learn it perfectly, travel to the past, and give it to your younger self. The symphony's origin is ambiguous. Neither you nor anyone else actually composed it. These paradoxes show that time travel, if possible, would create logical and causal puzzles. They suggest that the universe might have built-in safeguards preventing time travel. The Novikov chronology protection conjecture proposes that the laws of physics prevent time travel. Though general relativity permits it mathematically, quantum effects or other physics might prevent it practically. Now let's think about consciousness and time perception more deeply. When you're conscious, you experience a continuous flow of time. One moment flows into the next. Your consciousness moves through time like a boat moving along a river. But neuroscience reveals something interesting. Your consciousness doesn't directly perceive time. It perceives events and their sequence. Your brain infers time from the sequence of events. When you're asleep without dreaming, you don't experience time passing. 8 hours of unconsciousness feels instantaneous. This suggests time's flow is something consciousness constructs, not something directly perceived. There's a phenomenon called temporal binding, where your brain binds events that occur within about 100 milliseconds into a single moment. Events separated by more than that feel like different moments. The human brain seems to generate a specious present, a brief window of time that feels like the present. This window is only a few hundred milliseconds, but it feels unified, like now. Some neuroscientists argue that consciousness generates the present moment. Without consciousness observing, there is no present, just static space-time. Consciousness creates the flow of time by generating successive present moments. This connects to quantum mechanics, where observation affects outcomes. Perhaps observation creates the present moment. Perhaps consciousness plays a fundamental role in actualizing possibilities. This is speculative, but it suggests time's flow might emerge from how consciousness interacts with space-time, not from space-time itself. In physics, there's no flow of time. There's no process of becoming. There's just space-time, with events at different times. But we experience time flowing. We experience becoming, things changing, events happening. Some philosophers argue that becoming is real and fundamental, that time truly flows, that the present moment is special. It's what exists now, actualizing potentialities. Others argue that becoming is illusory, that space-time is static, all moments equally real, that our perception of flow reflects how consciousness samples space-time sequentially. Still, others argue that becoming is a way of talking about deterministic evolution. When we say time flows or things become, we're describing how systems evolve according to laws, not describing an actual flow of time. The question of whether becoming is real or illusory remains open. It depends partly on physics, partly on philosophy. Mathematical physics has revealed time's subtle role. In classical mechanics, equations of motion work equally well forward or backward in time. In quantum mechanics, time appears in the Schrödinger equation, which describes how wave functions evolve. But time is just a parameter. It's not treated as something fundamental. The equation doesn't explain where time comes from or why it flows. In general relativity, time is one component of four-dimensional spacetime. The metric tensor describes distances and time intervals, but all times exist equally in spacetime. There's no flow, no becoming. In quantum field theory, time is just a coordinate. Spacetime is four-dimensional, with time as one coordinate. Interestingly, string theory and other approaches to quantum gravity suggest time might be emergent. Time might not be fundamental, but might emerge from more fundamental structures. This would mean asking, what is time? Is like asking, what is temperature? Temperature isn't fundamental. It's an emergent property describing the statistical behavior of atoms. Similarly, time might be emergent, describing patterns in more fundamental physics. If time is emergent, what is it emerging from? What's more fundamental than time? Some speculate about timeless physics, where all physical laws are timeless. Time emerges as a way of organizing this timeless structure. Others speculate about quantum foam, a picture where space-time itself fluctuates at the smallest scales, and time and space emerge from these fluctuations. These remain speculative, but they suggest that future physics might reveal time to be emergent. Now let's think about experimental and observational perspectives. Physics is ultimately grounded in observation and experiment. What can we observe about time? We can observe that entropy increases. We can measure time's flow, or more precisely, measure the order of events. We can observe causality in action, causes preceding effects, but we can't directly observe whether time is real or fundamental. We can't observe the block universe. We can't directly measure the flow of time independent of observing events. So perhaps the question, is time real, isn't answerable through observation alone. It's partly a matter of interpretation. Different interpretations of quantum mechanics suggest different things about time. The Copenhagen interpretation emphasizes measurement and observation, suggesting time's flow emerges from measurement. Many worlds interprets suggest all possibilities exist in parallel, suggesting a static block universe. Cosmological observations reveal the universe had a beginning, the Big Bang, and is expanding. We observe entropy increasing. These observations support the idea that the universe had a low entropy beginning and evolved to higher entropy, consistent with thermodynamic time's arrow. But we haven't directly observed whether the future truly exists or whether the present moment is special. These questions might be beyond observational science. This brings us to the nature of time and reality itself. Is time real in some objective sense? Or is it real in the sense that it's how our minds organize experience? The answer might be both. Time might be real in how we experience and interact with the universe. The thermodynamic arrow of time is real in how systems evolve. But time might not be real as a fundamental feature of the universe itself. Time might be something like temperature or color, real in one sense, how the world appears to us, how systems behave, but not fundamental in another sense, not a basic ingredient of reality, but emergent from more fundamental physics. Future progress in quantum gravity might resolve the nature of time. A complete theory of quantum gravity might show time to be emergent or fundamental. It might explain time's arrow. It might solve the puzzle of initial conditions. But for now, time remains one of the deepest mysteries. The question, is time real, remains open, touching physics, philosophy, consciousness, and the ultimate nature of reality. The experience of time is so central to human existence that it's hard to question. But taking physics and philosophy seriously forces us to wonder, to question, to realize that our most basic assumptions about reality might not be accurate. And that's the beauty of science and philosophy. They push us to question, to wonder, to seek understanding of the deepest mysteries. Time might or might not be real, but the human impulse to understand time, to question its nature, to explore its mysteries, that's definitely real. That's what makes us human. That's what makes the pursuit of knowledge worthwhile. Let me explore some specific experiments and observations that reveal time's nature. One fascinating experiment involves the relativity of simultaneity. Two observers in different reference frames disagree about which events happen simultaneously. Imagine a train moving at high speed. Lightning strikes the front and back of the train simultaneously in the ground observer's frame. But in the train observer's frame, the lightning strikes aren't simultaneous. The strike at the front happens first. The strike at the back happens later. Which is correct? Both are. There's no absolute simultaneity. Different observers in different reference frames measure different times for events. This is a direct consequence of special relativity. This experiment shows that now isn't universal. There's no absolute present moment shared by all observers. Time is relative. Another revealing experiment involves time dilation. Atomic clocks on fast-moving airplanes run slightly slower than identical clocks on the ground. This has been measured precisely. Time literally runs at different rates for different observers. In strong gravitational fields, time dilation is even more extreme. Near a black hole, time runs much slower than far away. An observer outside could watch someone falling into a black hole appear to slow down and freeze at the event horizon. These experiments directly confirm that time is relative. It's not absolute or universal. Now let's discuss the physics of now more carefully. What does it mean for an event to be now? In our experience, now is the present moment. It's the moment we're experiencing right now. But relativity shows now is subjective. Different observers disagree about which events are now. In the block universe view, there's no special now. All moments exist. Now is just the particular moment in space-time where your consciousness happens to be located. In presentism, now is the only moment that's real, but relativity suggests there's no universal now, so which now is real. Some presentists argue for a preferred reference frame, a special frame in which now is defined. But relativity says no reference frame is preferred. Choosing a preferred frame contradicts relativity. The puzzle of now seems to suggest either abandoning presentism or rejecting relativity. Most physicists accept relativity, so they abandon the idea that now is special or universal. But this is philosophically disturbing. Now feels special. It feels like there's a real present moment. The idea that now is merely subjective, observer-dependent, seems wrong. Yet the physics is clear. Relativity demands this conclusion. Some physicists and philosophers argue that quantum mechanics might restore a universal now. Some interpretations of quantum mechanics involve a fundamental wave function collapse that happens instantaneously everywhere. This could define a universal present moment, but this remains speculative. Standard interpretations of quantum mechanics don't require or suggest a universal present. In quantum mechanics, the Schrödinger equation describes how wave functions evolve over time. The wave function contains all information about a quantum system. It evolves deterministically according to the Schrödinger equation. But when you measure the system, the wave function collapses. It jumps discontinuously to a measurement outcome. This collapse is irreversible and creates an asymmetry, a direction of time. Before measurement, all possibilities exist superposed in the wave function. After measurement, one outcome is realized. This one-way process from possibility to actualization defines an arrow of time. Some argue that measurement-induced collapse is the source of time's arrow. Others argue that decoherence, the gradual loss of quantum coherence due to environmental interaction, explains the arrow without invoking collapse. But these explanations themselves require understanding what measurement is and when decoherence occurs. They push the question back without fully answering it. The nature of time in quantum mechanics remains puzzling. In quantum field theory, time is treated as a coordinate in four-dimensional spacetime. Fields exist at all spacetime points. Particles are excitations of fields. The theory is time-symmetric. You can run it backward and get valid physics. Yet observations show time's arrow. Some physicists argue that time's arrow in quantum field theory comes from thermodynamics and cosmology, not from the theory itself. The expanding universe and increasing entropy provide the arrow. Others argue that we don't fully understand time's arrow in quantum field theory. The question remains open. In string theory and quantum gravity approaches, time's role is even more mysterious. In some formulations, time is emergent. In others, space-time itself is emergent. The very notion of time might be approximate, only valid at large scales. These theoretical developments suggest that time's fundamental nature might be revealed only by a complete theory of quantum gravity. When you're fully conscious and engaged, time seems to flow naturally. Hours pass unnoticed if you're absorbed in something interesting. But time perception is malleable. When you're bored, time seems to drag. When you're anxious, time seems to speed up. Time's flow is subjective. In certain meditative states, practitioners report experiencing expanded or altered time perception. Time seems to slow down or become more vivid. Anesthesia provides a striking example. Under general anesthesia, you're not conscious. Time doesn't seem to pass at all. 8 hours of surgery feel instantaneous to you. These observations suggest that time's flow is intimately connected to consciousness. Without consciousness, there's no experience of time's passage. This has profound implications. If time's flow emerges from consciousness, then perhaps time isn't a feature of the universe itself, but a feature of how conscious beings experience the universe. There's a thought experiment called eternalism and the block universe of experience. Imagine a static, unchanging universe, a block of space-time containing all events. A conscious being moving through this block would experience time flowing. It would remember past events and anticipate future events. Yet the universe itself is static and unchanging. This suggests that the experience of time, time's flow, can emerge from consciousness interacting with a static space-time. The universe need not have time's flow built in. Consciousness creates it. But this raises a deeper question. What creates consciousness? Is consciousness also part of the static block? If so, how does it create anything? This touches on mind-body dualism and other deep philosophical problems. It suggests that understanding time requires understanding consciousness, which remains one of science's greatest mysteries. Now let's discuss some specific philosophical positions on time in more detail. Presentism holds that only the present exists. The past is gone. The future doesn't exist yet. Only now is real. Presentism matches our intuition, but it has problems with relativity and distant events. If only the present exists and different observers disagree about which events are present, then what determines what the present truly is? Some presentists accept this and argue that the present is observer-dependent or reference frame-dependent. But this seems to undermine the idea that the present refers to something objective. Eternalism, or the block universe view, holds that all moments, past, present, and future, exist equally. Now is just the moment you're currently located in. Okay? Like here is the location you're currently at. Eternalism is consistent with relativity. It explains why different observers disagree about simultaneity. They're just in different parts of spacetime. Like people in different locations might have different perspectives, but eternalism seems to deny that anything changes or becomes. If the future already exists, how can you change it? How can you make a free choice? Eternalism seems fatalistic. Some defend eternalism by distinguishing between the universe being static, all moments exist, and our experience of time flowing. They argue that even in a static universe, we can experience time flowing. Our consciousness moves through the block, experiencing successive moments. Growing block theory holds that the past and present exist, but the future doesn't yet exist. The present is the edge of the growing block, where new moments come into being. Growing block combines elements of presentism. Only present and past are real. And eternalism. Past is not erased, but persists as real. If presentism is true, then the future doesn't exist. Your future is genuinely open and undetermined. This supports libertarian free will, the idea that you can make free choices that aren't determined by the past. If eternalism is true, then the future already exists. Your future is already real, even though you don't know it yet. This seems to support determinism. The future is fixed. But some argue it's consistent with free will properly understood, since free will is about your choices determining outcomes, not about outcomes being undetermined. If time is emergent, arising from more fundamental physics, then time's nature depends on what's more fundamental. Understanding time requires understanding quantum gravity. These implications show that the nature of time isn't merely academic. It touches on questions of free will, determinism, moral responsibility, and the meaning of life. If the future is already real, does it matter what you do? If the past is gone and unchangeable, must you accept it? These questions connect time's metaphysics to ethics and meaning. Let's think about time in everyday life and how our understanding has changed. In our daily experience, time seems objective and uniform. It flows at the same rate for everyone. The past is gone, the future is coming, the present is now. But our intuitions about time are shaped by our limitations. We move slowly compared to light. We live in weak gravitational fields. We experience timescales from seconds to decades, not microseconds or billions of years. In these limited regimes, Newtonian physics works well. Time appears absolute and universal. But at extreme regimes, near the speed of light or in strong gravity, time behaves strangely. The universe's true nature, revealed at extremes, contradicts our intuitions. This is a pattern in science. Our intuitions, shaped by everyday experience, are often wrong about how reality works at extreme regimes. We thought space was flat until Einstein showed it's curved. We thought determinism was certain until quantum mechanics revealed randomness. We thought time was absolute until relativity showed it's relative. Each revolution in physics required abandoning intuitions and accepting counterintuitive truths. Understanding time requires doing the same. We must abandon the idea that time is absolute or universal or flows uniformly. We must accept that time is relative, that now is subjective, that time's nature is subtle. This is difficult. It's hard to fully believe that the future is already real, or that time doesn't flow, or that consciousness creates the present. But taking physics seriously requires accepting these conclusions, even when they contradict intuition. Finally, let's consider what questions remain open and what future physics might reveal. The origin of time's arrow remains mysterious. Why did the universe start in a low entropy state? This seems to be a brute fact about our universe not explained by physics. But future cosmology might provide an explanation. The role of consciousness in time remains unclear. Does consciousness create the present moment? Is consciousness fundamental to physics? We don't know. The fundamental nature of time might be revealed by quantum gravity. Does time emerge from more fundamental physics? Is time discrete or continuous? These questions await a complete theory of quantum gravity. The relationship between time and entropy might be even subtler than we understand. Could there be circumstances where entropy decreases while time flows forward? Could time's arrow differ in different parts of the universe? These open questions show that time remains a frontier of physics. Despite centuries of progress, time still holds deep mysteries. Let me explore some specific thought experiments that illuminate time's nature. The light clock thought experiment is useful for understanding time dilation. Imagine a clock where light bounces back and forth between two mirrors. The time for one tick is the time for light to travel from one mirror to the other and back. Now imagine this clock moving at high speed. From the perspective of a stationary observer, the light has to travel at an angle because the mirrors are moving. The path is longer, so the light takes longer, so the tick takes longer. From the clock's perspective, it's stationary and ticks normally, but the stationary observer sees it ticking slowly. This thought experiment demonstrates that time runs at different rates for moving observers. It's not just a matter of perspective. The moving clock literally ticks more slowly. The twin paradox is another revealing thought experiment. Imagine twin sisters, Alice and Bob. Alice stays on Earth while Bob travels on a fast spaceship and returns. Bob ages more slowly than Alice due to time dilation. When Bob returns, he's younger than Alice. This seems to violate relativity symmetry. From Bob's perspective, Alice was moving, so shouldn't Alice age more slowly? The resolution is that Bob's reference frame isn't inertial. Bob accelerates and decelerates when launching, turning around and returning. This acceleration breaks the symmetry. Alice remains in an inertial frame, Bob doesn't. When you account for the acceleration properly using general relativity, Alice ages more than Bob. The paradox is resolved, but it shows that acceleration matters for time dilation, suggesting time isn't simply relative but depends on non-inertial motion. The rubber sheet analogy helps visualize space-time and time dilation. Imagine space-time as a flexible rubber sheet. Massive objects warp the sheet. Time runs slower in regions of deeper warping, stronger gravity. This analogy captures the essence of general relativity. Gravity isn't a force, it's the curvature of space-time. Objects follow geodesics, straight paths through curved spacetime. Time's behavior in curved spacetime, near gravity, is more complex than in flat spacetime. Time runs slower in deeper gravity, faster far away. The information paradox thought experiment involves black holes. Imagine matter falling into a black hole. In the outside observer's frame, the matter appears to freeze at the event horizon, but information hasn't actually fallen in yet. It appears to hover at the edge, infinitely redshifted and dimmed. When the black hole eventually evaporates through Hawking radiation, the information that appeared to hover at the edge is lost. Classical matter information is gone. But quantum mechanics says information can't be destroyed. This is the information paradox. One resolution is that information is encoded in correlations in the Hawking radiation. Another is that information doesn't actually cross the event horizon. A third is that quantum mechanics breaks down in black holes. Each resolution has implications for time and information. Again, time is symmetric. Time reversal, t to minus t, leaves many theories invariant. This mathematical framework shows that time's role in physics is subtle. Time is a coordinate like space. Time is not fundamentally privileged or different from space in most physics equations. But somehow time has a direction in experience and in observations. Reconciling time-symmetric fundamental laws with time-asymmetric observations remains a major puzzle. Let's discuss Wheeler-DeWitt equation and quantum cosmology more carefully. In quantum cosmology, physicists try to apply quantum mechanics to the entire universe. This requires dealing with gravity quantum mechanically, which brings in the infinities and divergences that plague quantum gravity. The Wheeler-DeWitt equation describes the wave function of the universe. Remarkably, this equation has no time derivative. It's not an evolution equation, but a constraint. This means the wave function doesn't evolve in time. It's static, timeless. This suggests that time doesn't appear in fundamental quantum cosmology, but we clearly experience time. How does time emerge if the wave function of the universe is timeless? One proposal is that time emerges as a semi-classical approximation. In the classical limit, space-time emerges with an apparent time direction. But fundamentally, there's no time. Another proposal is that internal time emerges. Degrees of freedom in the universe can be used to define a notion of time internally, even though there's no external time parameter. These proposals are speculative and controversial. They suggest that time might not be fundamental, but emergent in quantum gravity. Now let's think about time and the mind from a neuroscientific perspective. Neuroscience reveals that time perception is constructed by the brain, not directly perceived. Different brain regions handle different timescales. The cerebellum handles sub-second timings. The basal ganglia handle longer intervals. The cortex handles abstract temporal reasoning. When these regions are damaged, time perception is distorted. Some patients lose the ability to estimate short intervals. Others lose the sense of temporal order. They can't tell which events happen first. This suggests that time is assembled from multiple neural processes. There's no single time sense like sight or hearing. Temporal binding, mentioned earlier, involves the brain binding events within about 100 to 500 milliseconds into a single perceived moment. This window varies with attention and arousal. When highly attentive, the window shrinks. When tired or distracted, it expands. The subjective present is this temporal binding window. It's not a true point in time, but a window of integration. The brain collects information over this interval and presents it as a single now. This neural perspective suggests that time's flow, the present moment, and time's direction are constructed by the brain, not discovered in the physical world. But constructing something doesn't make it illusory. The brain constructs color from wavelengths, but colors are real in how we experience the world. Similarly, the brain constructs time, but time might be real in how we interact with the world. This connects neuroscience to physics. The physics of time is about how time works in spacetime. The neuroscience of time is about how brains experience and construct time. Both are important for understanding time fully. Time is central to human experience and meaning. We mark time with rituals and celebrations. We structure life around temporal cycles. We plan for the future and remember the past. Our sense of identity is tied to time. You're the same person over time, with memories connecting past to present. Free will involves choosing a future that's not fully determined by the past. Mortality is a fact of time. We grow old and we die. Death's inevitability gives life meaning. Time is precious because it's limited. If time isn't real, or if the future already exists, or if time is emergent, these have implications for how we understand ourselves and our place in the world. Some find comfort in eternalism, the idea that all moments exist. Death isn't an end, but just moving into a different part of space-time. Your younger self still exists somewhere in space-time. Your loved ones who died still exist in their times. Others find this cold and meaningless. If everything already exists, why does anything matter? Why should we care about the future or strive to create something? But this is a confusion. Even in a static block universe, our choices matter. Our choices determine what happens in the future. The future exists, but it exists because of what we do. In a real sense, we create the future by acting now. Understanding time's nature doesn't necessarily diminish meaning. It might deepen it. Recognizing that time is subtle, that past, present, and future are more interconnected than we thought, might broaden our perspective. The study of time reveals that reality is far stranger and more wonderful than everyday intuition suggests. It invites us to expand our understanding, to question our assumptions, to see the world with fresh eyes. This is the true value of science and philosophy, not just to answer questions, but to inspire wonder and deepen understanding. Thanks for watching.